let's get started here. So we're going to try to refresh our memory some more about how MiniSat was working. Let's just do open recursive, I can't remember the name of this. Open all code recursive, there we go. And then, let's see, the key idea here was, I think it was in the solver. Propagate. So what the solver is up to here is it's made a new guess, or it's the beginning and it's got some initial guesses. But either way, it's got some guesses and it's trying to go and figure out if there's anything it can logically deduce given the guesses it's made about other things that would have to be true. Blocker. If the value of the blocker is true, so if we propagated not B and then we saw this, that would not get hit because we would go 3B. Oh, that's false. So that's not so the blocker doesn't do anything here. We would make sure the false literal is data 1. So we would look at, here's the clause. False literal P. Where's P coming from? P is enqueued, fact to propagate. Okay, so we're not actually using the variable here to compare against this. We're using the variable we're propagating. So if I came in here and I was propagating C, I would go to 3, and I would in fact still find a C here. I don't know what you mean, Brett. Have I checked the... I don't know what you mean. But anyway, point is, when I go to propagate the C, the B here is the blocker, does not have to be the thing that it finds. It'll always be the case that the watches for 3 live in the correct locations to match the two things at the beginning of the clause. So if C and D are at the beginning of the clause, then C and D will be the locations where I find the watches for 3. That's the trick. The blockers are extra. They're a little extra. They're a little extra trick. Now, that's not to say that I think the algorithm would still work without them. That might not be the case, but I don't entirely understand why it wouldn't work without them. Like, if I didn't have the blocker here, you would just continue through the rest of this, and as I remember, the rest of it would still end up finding, like, you'd sort this thing here, and if we have a blocker, we just save it there. So I think all the blockers are doing is, remember, we're trying to sort these things to the front. If they are undetermined. If they become true, then we don't want to keep looking at that clause. So that makes sense. And so if anything in the clause is true, it's probably trying to arrange for one of those first two to be true. So we can check if the entire clause is true. just by looking at the first two is the hope. But how would that, like, say I had happened to propagate something that would make a clause true, but wasn't reflected in the first two variables? How would that still work? What does that mean? In Q a literal, unchecked in Q. Okay, so it's just putting something onto the Q. I don't actually know what the simplifying solver does. We haven't looked at that at all. But I don't want to get caught away into that. So what I'm looking for is just to recall and understand a little better how the propagate works before I move on. I had this mostly pretty well in hand last time, and I think I got most of what I had before back. I'm just trying to make sense of... Oh man, it's a little bit like the code doesn't want me to understand it when I read code that's like all crunched up in all these ways, and I don't know. It could just be that the algorithm is complex, but I get the feeling like this just defies simple understanding by being the way it is. This jargon, I don't have a jargon dictionary, so I don't know exactly what unit under assignment means. I think it means that there's only one literal left. Kind of, but it doesn't even necessarily mean that, because they're now, it's like, it's critical and in my jargon, maybe? I don't know. Okay, let's see. This is the loop of k from 2 to the n, so this is looping over the parts we don't have. If they're not false, then it's either true or it's undetermined. In either case, we can swap that up to the front. So what happens is that takes the spot of the thing that is no longer true, right? C1 is the spot where we were storing the literal that's been negated out. So this one can't be relied on, but we're swapping it out with we're swapping it out in the list of literals with one that is not yet determined as false. It's either undetermined or determined as true. And then let's see here. Um, this puts it on the list of watches. For whom? Whose watches? The all watches? Right, watches is like a map thing. So we put in an index there saying this is the new spot where the watches live, where the new watch lives, and then we put the watch there. So the watch is the one we erased up here. Okay, and so then what's happening here is if we weren't already hitting a blocker that let us know that this thing was true, then by here we'll find out, because here we're going to check the other thing at the front of the clause. So by this point, if one of the two things, if we got lucky, we will find out that the clause is true and we'll be done. But then here what we'll do is the thing we're propagating, we'll make sure it's in slot 1. We're about to figure out what to do about the fact that this is false now. Yeah, Young Lane, I do complain about code style sometimes, and I don't mean to diss on these as in the people did a bad job or anything. This might have made a lot of sense in their context, but the sad thing about SAT solvers is that I can't find any code that is both easy to build and read in from the perspective that I come from. And so that is frustrating. It feels like it's work that has to be done again. And I can't find any good explanations in any format that I can understand, sadly. The best explanations are some of the English ones, but there's a lot of detail in the code of things like this that aren't out there in a format I can find, besides code like this. And so I complain just because it's it's like someone knew this stuff, and the transfer of information happening here is so poor that it is frustrating. Even if it's nobody's fault, it's frustrating to me. And so the complaints come. But anyway, the thing here, I think, is that I think this makes sense. It's just it's just slightly hard to put a finger on the whole picture at once. So this blocker, if it's true, then we come out. But otherwise, imagine the blocker is irrelevant. I think we can think of it that way. It's just it's a happy accident when that speeds things up. Otherwise, we know we're trying to propagate that C1 is false, or that one of the two first literals is false, so we swap it to the C1 slot. So we know the C1 slot is false. Hopefully the C0 slot isn't, although it's not impossible. It could be that C0 will be false too, but that's sort of an unusual special case, not a bad case, not unexpected, just one that we would. It's a particular shade of the algorithm that we don't need to think about as the default case. Like when we're first starting off running this, the other one won't be that way. It won't be until quite a bit later into running it that could happen. And then we look at, so first becomes whichever that other one was, the other one in the pair of the first two that is sort of, we're imagining hopefully is undetermined or true. And we take a look and see if it's true. Now, if it was already the blocker, then we've already determined it's not true, so no need to evaluate. So this is just to avoid evaluating twice. Then we run the evaluation. The evaluation, if it comes out as true, tells us that this clause is fine, and we just stop there. We keep the watches as we had them. We don't sort anything differently. We now have a true and a false in our first two slots, and that's fine. We said we want to keep undetermined things in those two slots, but once one of them is true, we're good. We're using these two as an accelerated view onto the whole clause, and if one of them is true, then there's no need to change that view in any way. Now, what we do is if the other one isn't true, it's either false or undetermined. So we are now in a situation, though, where we have a false or undetermined slot in C0 and a false in C1. And we're going to then scan through the rest of the clause and look for anything else that is not false. So if we find something true or undetermined, that is more useful, and we want to get it in there and swap the thing out that's definitely false with that thing that's true or undetermined. So we look ahead, and we grab one of those things, and we put it into the watch list in the appropriate place given the structure of the watch list and the clause literal data structure and the way they're supposed to relate. So we just keep that, we maintain that data structure based on the simpler principles I've already outlined about that. And then after that's happened, we take a quick look at this. So if that's happened, we're done. We have wiggle room. It's either completely satisfied or there's potential for it to be satisfied. Either way, we have wiggle room and we leave it there for now. What I don't get about that is, okay, that's right. We have wiggle room. We have wiggle room because, like I said, C0 is either true or it's undetermined, and then the other one we took is either true or undetermined, and so there's no, it's not critical. But if we don't find anything to bring to the front, then we check if the first value is false. So we've been saying the first value is either true or undetermined, but it could be false, and this is where I get a little confused. If this is false, then the clause could already be critical, and we won't notice, because if we find something undetermined deeper in the clause, we shuffle it to the front and we just say we're done. So it could be that we could have propagated from this clause, but maybe the point is that we don't need to, or that we'll discover it, we're guaranteed to discover it another way. But I'm not sure. Either way, what definitely happens is if we don't find something, then we have a false here in the second slot, true, false, or undetermined in the first slot, and we check and see if that thing is false, and we didn't find anything else in the clause that wasn't false, then we found a conflict. On the other hand, if that first guy there is not false, then we enqueue that we need that to be true. That has reached the critical, then we know the clause has reached the critical state, and it's this first one that has to be propagated. The part where we miss it that gets confusing to me is, what if the thing that is the only undetermined variable in a clause that is otherwise completely false is the one we swapped here, and then we skipped over this part. That part confuses me. In that case, we would go to the next clause in the list of watches. Yeah, it just seems like you'd never get a chance. So here's what I'm thinking. I think I have the algorithm down as far as I possibly can. I'm not going to be able to 100% verify that I know this algorithm without being able to visualize it. And I'm not going to be able to visualize this algorithm any better than what the debugger can do, which I've already done before. It's quite hard to get the debugger to visualize this nicely. So I think I get propagate, at least in terms of what the code here does. Why it works is a little confusing, but Young Lane asks, is it more difficult to search and find functions that look like foo.update rather than foo update in forcoder? Yeah, a little bit. So like if I want to find all the occurrences of propagate, I can do that, right? And that's just because they only have one function in this code base called propagate, no matter, like, there's not different objects with it. If I want to find the definitions, there's not really a problem if I know what, like, the class and the method I'm looking for. But usages can be a little bit harder if people are using really short function names, right? If they're using these really short function names and you try to find them and they're being used on different object type, like different classes have the same short object name, or short method name, and then you go and find some place where it's getting called on an object, the name of the object itself doesn't tell you what type of object that is. So it becomes this sort of chain of extra lookups you have to do to even verify that you're looking at an instance of a function call of the thing you care about, and so that part can suck. And that's not even really the worst part about it. Like, I haven't had a lot of trouble in this process from that problem. Other things that are bigger problems are like, there's no clarity here on what is directly dependent on. So unchecked in queue, it takes in a first and a CR. What does it do though? Like, what does it operate on? If it had to take in a parameter that was like propagation queue, right? Then I could see right here that, oh, this is the kind of thing that modifies the propagation queue by having this data. But object orientation means that you can hide all of the things that are that you decide are convenient to hide about the parameterization. So the unchecked queue, I can come over here and it says something like, okay, let me give myself a little space. In queue, a literal assumes value of literals undefined. Oh, well, that doesn't help at all. So then we can like track down where is this defined. So unchecked and queue is defined right here, and we see like, oh, it's this assigns and this var data. Okay, so that we are assigning to the literal p, and we have this from clause. Okay, so these are the things that are getting affected. And we go, wait, so that those must be members of this class here, and then we track down the type, right? And the type information of what assigns is would have had to have been put here, right? You would have had, like, if this was not allowed to be object-oriented, you would have had something like this, right? And so just you can see that in object orientation, the number of steps it takes, the style allows you to write code and encourages you to write code in a way where when you go to read it, the number of steps you take to make sense of tiny little artifacts is tremendous. One tiny little artifact can have hidden inside of it all sorts of implications into other parts of the code base that are implicit. And the tracking down of all of that to understand it can be really tiresome. And it makes a big difference when it's in like a C style. You can just like go, oh, I need to find out how this data structure is laid out. And I can see that this is going to modify one of those, right? And it's just all right there in the function. And this was written in 2005, so probably at like somewhere around the peak or a few years before the absolute peak of people really pushing object-oriented programming on like making it, trying to make it do everything. Trying to make it work. In especially this like C++-y object orientation kind of thing. I think it was certainly the period of time when I was writing code more like this all the time. Anyway, on the flip side, this is one of the better open source solvers in terms of solution quality that's been made available for free. So there's something in here to learn. It's encoded in an arcane dialect of logic that I do not easily speak. Now, I think that propagate, I'm happy enough with that. That's kind of where I'm landing. So there's another big function here in the solver that I felt I needed to spend some time on. Interesting. So they have an idea of reducing the number of learned clauses over time. That's interesting. I'm curious where that gets called from, just as an aside. Let's take a look. Okay, right here, search. Search for a model. The specified search for a model. Right, this is where there's like comments that aren't quite fully grammatically useful. Use negative value for no number of conflicts indicate in. Okay, so search for a model, the specified number of conflicts. This takes in search number of conflicts. Use negative value of number of conflicts to indicate infinity. I think this is like the actual solve. The solver, the search, this is like the limit of how many conflicts to tolerate before you give up. And if you make that infinity, it means just keep running for me, don't give up. So yeah, if the number of conflicts is non-negative, and if the number of conflicts we've seen is greater than the budget, or we're not within the budget of some other budget, here we have no information at all. It's completely hidden what this is a reference to. Then we've reached bound on the number of conflicts, progress estimate, cancel, and return. So it returns that it did not decide whether or not this is satisfiable, and some sort of progress estimate, like how far it thinks it got into solving it. But let's read how the search works. So propagate at first, that makes sense. The first thing you do is if there's anything in the structure that you can immediately deduce, you find that out first. And then if you found a conflict, so this here says if the conflict is not undefined. In other words, if we did in fact return a clause that has a conflict, then what we do is this. So remember, this is a loop, so we're not necessarily at the beginning of the algorithm whenever this happens. But if the decision level is 0, what that means is we haven't made any guesses yet. We deduced a conflict from the ground level structure, and therefore there's never going to be a way to make this thing satisfied. There's just some direct, like, A and not A both have to be true, and therefore the whole thing will never work. So you find out that it's not satisfiable right there, and you're done. The next thing you do is you learn a clause, and so analyze is how you learn your clause. I think that was one of the things I needed to learn more about. How does this solver build its analyze? So it analyze, looks at the conflict, fills the learned clause, and fills a backtrack level. So these are output parameters. Again, C++ style lets you make everything look like an input parameter instead of having like. Honestly, what would be great is if from the calling side you had to like annotate them like that. That would be even better. But at least in C-style, it would be like this, indicating that probably those are returns. Anyway, cancel until. So cancel until is their way of rewinding the decision stack, right? So there's this growing stack of decisions that have been made, guesses that have been made about how to assign certain variables, and after a conflict gets reached, we learn some information in the form of a new clause about the problem, and we backtrack. We backtrack to a point. We backtrack to a point. Well, that's the part that's always confusing. We backtrack somewhere to where we can begin making guesses again. And the way that this backtrack tends to get implemented confuses me, because I would expect that it needs to backtrack to the most recent guess that was implicated in the conflict. But it tends to backtrack all the way to the earliest guess that was implicated in the conflict, removing everything except for the very first guess in the conflict. And that seems confusing to me, because like if I think about what you know from assumptions and stuff, it's still like, isn't it possible that the last guess was the only thing you needed to change? And if you were going to think about it the other way and say like, look, all of these guesses would have been made differently now that we've learned of this clause, then why don't you also revert the very first one? But I don't know. It might be that I've been misreading the situation from the code a little bit. I need to read this one in particular more closely. But then, yeah, cancel until does the actual backtracking. Then we look at our learned clause. Sometimes our learned clause just tells us that we've learned about how a variable needs to be assigned, and so we enqueue that. Otherwise, we bump activity. I don't know what that means. Increase a clause with the current bump value. What? Okay, so this is quite simply it's saying we have a, oh man, they're returning a reference to the activity of the clause. Okay, anyway. Basically, this is a variable that is being incremented, and then if it gets too big, we scale down all of the clause's activity counters, because these are being implemented with floats, so that if one of them gets very, very big, we can maintain the ratios between all of them and scale them all down equally, and then we also scale down the increment amount. So it's trying to use its precision to keep track of the most active stuff as accurately as possible. Young Lane, yes, I have my own sat solver, and I'd kind of like to get a chance, maybe today, I'm looking for maybe a shorter stream, but I might take like 1 hour to do some code reading and then switch to sat solver. So I think I'll show off a little bit of that today, and also talk about what I'm going to try to build with it next. I have two big ideas, basically. One is to build a single header library sat solver for C. And the other is to build a visualizer to go with it, so that you can visualize, like to literally render out the algorithm running. I think that those two projects would be fun little sat projects, with the visualizer being like a cool educational / understanding implement, a method of understanding your sat solver. At the most extreme end, it's a supplement to the tool, which is to help you understand your sat solver and what it's doing in some ways, and reduced from that, taking a step back from that ambition, the other goal of it would be to just help with explaining sat solvers. And then the other project, making the single header library, I would want it to be like you could actually relatively easily throw it into your own C code and start playing with it. And I haven't gotten very far on either of those yet, but I've written a sat solver that is not a library, that is just thrown on top of my code base, and I'd like to iterate on that today, probably for a little bit of time. I have some other ideas, but I'm not entirely convinced that they require a sat solver. It might be that they require sat solver, that they would build on some of the same muscles a sat solver builds on, but they are not actually good ideas that require a sat solver. So I'm going to hold off on those until I understand those more vague ideas better. I'm going to hold off on talking about those things I'm not ready to actually explain fully. Okay, so we know what the CLA bump thing is doing. That's how we keep track of a clause. So when we create a clause, CAC, so that we get back the reference, we put that in the list of learned clauses. We call attach clause. What is that doing? So attach clause is what it really means is put the watches in. So this is another problem with this code base, is like the naming here is the interface attach clause it's like that interface is designed specifically to tell me nothing about what's happening inside that function. That's how it feels, right? Attach clause. Well, I understand we already put it on the list of learns. In what way is it not attached? Oh, it's not attached to the watches. And it's not attached, we don't have the number of, we haven't incremented these counters and stuff like that. Okay, great, but like, why hide that? Why hide that that's what this is actually doing with a name like attach clause when there are other things you have to do to attach clause? Anyway, it's a little confusing. But anyway, we put it on the list of learns, we attach it to the system, attach it to the system, we bump the activity, as in we just increment it once. We say, hey, this just got learned. Let's pay some attention to the one we just learned. And then unchecked in queue, learned clause 0. So the first thing it does is it uses the learned clause to make a guess. So here it's forced because there's only one literal in a clause, so there's no need for a whole clause. We just have to make this work. But here is making a guess, and that guess is based on just taking the first thing that happens to be in the learned clause and making it true. So presumably, just to make some sense out of this, presumably I think what we could probably learn from this is when we get a conflict clause, remember, the clause isn't going to be a big complex logical concept, right? Because a clause is just a bunch of literals ORed together. It's just a big OR block. It's just a chain of ORs, right? It's like A or B or C. Or it could be A or not B or not C, right? It can have nots. We can have negations at the level of, like, at right inside those ORs, but that's it. And so the new clause isn't really a big complex concept. If it tells us something, it makes sense that what it must be telling us is that one of these things must be true, right? That's all it's saying. It's saying one of these things must be true. And in order for us to have learned that, probably it makes sense to assume that that sort of thing is the kind of thing you learn when before they were all false, and that created a problem. So if they were all false before, and then we've rolled those guesses back, then making this guess next makes sense, because it's just saying, okay, previously we got ourselves into a knot by making all of these things false. Then we learned a clause, and that clause contains a necessary condition for making the whole thing satisfiable. Not necessarily everything we need to know, right? There's still a lot of other stuff we might need to figure out, but so it's not sufficient. And it's not necessarily the case that the whole thing is satisfiable anyways. But if it is satisfiable, then it's necessary that this clause that we've just learned will be true along with the rest. And so since we just learned it, we take one of those and we make it true instead of false, like it must have been when we found the conflict, right? And by true, I don't mean we make a variable true. I mean we make a literal true, which might actually mean making a variable false. But we make sure that this new thing we've learned will work out by this, as a new guess. Now that might not be the correct thing to do, right? That's just a guess, because it might be that the correct thing to do to satisfy the whole formula is hidden somewhere farther down in the clause, but it's a good guess. It at least gets us going down a novel path. We decay activity. So the decay of activity I do recognize. We have those activity bumps, so we just looked at that, which is telling us what to pay attention to. And as we increment it, we're sort of scoring which things are important. And then we decay everything. We constantly are shrinking everything's relevant score by keeping the ratios the same but shrinking it. And that is relevant when we go to increment again. We're incrementing by the same amount. We don't decay the increment amount when we do this. So we are sort of scoring things, and then we shrink and score more and shrink, and the scores are always like full increments, and then the shrinks make them less important over time, so that more recent things are constantly dominating the attention of the activity tracking system. Okay, so this is just some kind of counter. I don't know. When we begin the solve, we take learned size, adjust confl, and store it as the counter, and we decrement the counter, and then we increase this. By a certain amount. Okay, so this is just, so what this is missing that it should have is this is for, I'm going to start marking the code up, I think. I've been precious with it up until now, but I think I'm going to start inserting myself into this code so that I can get a stronger handle on it. This is max learns. Every time we learn something, we decrement this. If we get to 0, we increase the timer to when we will run this path again. We reset the timer to the new max, like the new length of the timer. So it starts counting again. And we increase this max learns. I don't actually know what max learns is doing for us. So if the number of learned clauses minus the number of assignments ever gets over this maximum, we do the reduction right there. So this is number of conflicts, conflict within budget, reach bound on number of conflicts, progress estimate. Yeah. Okay. So nothing here is particularly surprising to me, is the thing. Like, all of this is sort of like just at more and more work optimizing this. This is like, I don't really know what to write here. It's not just for printing, but it's the, Okay, the control parameter. That I'm talking about is max learn. So adjust max learns over time. So if then, here's what happens. If we ran propagate and we did not get a conflict, we end up here. And here, weirdly here when we didn't get a conflict is when they're checking if we've blown past the budget. They don't. They don't do it up here when they're actually noticing conflicts, which is just strange to me. Here we increment our conflict, and usually I would think if you're gonna have, hey, check if we've gotten too many conflicts, that you would put it there where you're incrementing it, and instead they're putting it here where there's been no conflict. I don't know why that choice was made. Simplify the set of problem clauses. So this is just a trick that says if we did a propagate and we haven't made any guesses yet, then we might have fixed some variables. Simplify reduces the number of clauses that we actually are treating by doing things like saying, hey, if a clause is already satisfied, pull it out because the variables are set to make that work. And at this stage, since it's decision level 0, we haven't actually made any guesses yet. We've only propagated hard facts of this system. We haven't made guesses about how to solve the whole problem. And so the things that the things that we are forced to conclude, just given the structure of the problem, aren't changing and can't be guessed into different formats or anything. So we might as well bake in everything we've learned from that propagation, since we won't be rolling any of that won't be something we need to be able to roll back anyways. Here we do the thing where we reduce the number of learns, probably so that as things run for a long time, things we learned early on don't sit around slowing down the algorithm when they're not really the focus of what it's iterating on anymore. Something like that. Here we have provided assumption. So here we have, at the very beginning, we propagate decisions we propagate information that is completely no guess is made. Here what we're doing is the user can assign some assumptions into the solver, and so as long as we are at a stage where we haven't actually made all those assumptions, what it's going to do is I don't know what analyze final is doing. I do need to go back and read the analyze part. That's where the interesting thing is. But yeah, this part makes sense. It's saying just fill this up with assumptions. If the assumption the user wants to make has already been determined by something like the propagation, then we just sort of humor that and say like, yep, we made that decision. Increment this counter here so we can get closer to finishing all of the assumptions. If we've seen that has to be false, then we have an unresolvable conflict because the user wants us to assume it's true. We've already deduced that it's false, either from previous assumptions we've propagated or from this core structure of the problem itself. So we can't make this assumption true, so we're going to return false because their assumption makes this unsatisfiable, and give them the final analysis. Need to learn about that. And finally, if it's undetermined, then we just determine that that is the literal we're going to guess next, is the one from the assumption. And in these two cases, we don't loop and finish all of them. For this true case, we keep looping because like nothing stops us from just skipping over those. Now the issue is we might not have had an assumption, so then we come down here and say if we still don't have an idea of what to do next, instead we'll pick a literal using a heuristic. So this is the heuristic. That's the other piece we might want to study. Next, model found, return true, increase decision level, new decision level, and we in queue. Okay, so let's learn about this part. So if they roll a random number, so they roll a random number here and they say, is that like a random double? drand, yes, drand returns a double. Okay, so we roll a double, and if it's less than the random variable frequency, which is probably just a parameter in the system, yep, control variable kind of thing. So if we get a heads, let's say this is a coin flip, and we can set the P, this is the P on the coin of the probability of a head. And so if we get heads on our coin flip, and we can set that to 0, so it would eliminate this possibility entirely, which I think is the default, or it can be like 50-50 or 10% or whatever. So if our coin and get a heads, and if the order heap is not empty, then random seed, order heap size, value next, undefined, and decision next. So what they're trying to say here is this. So if we flipped ahead and we have some variables in the order heap, then we take one, and it looks like we just uniformly, doesn't matter how far up or down the heap it is, we just take one, right? Any all equally likely. And what is the decision? Declares if a variable is eligible for selection in the decision heuristic. Gotcha. So if we can select this variable, then we increment the number of random decisions, and it has to be undefined. And then, okay, yeah, so this is like validity, and then it goes, okay, while this is still not valid, so either we have something that is undefined, or it's not valid for for heuristic selection, or the value of the thing we picked is itself not undefined, right? So we have an undefined variable, or the one we picked is, or the variable we picked is defined, is a good variable, but the value of that variable is already fixed, then we can't make a guess to change it. And we also want to check if this one, if the variable we've picked a variable, it's not defined, but it's not eligible for heuristic selection, then we go. Right. So here, what they mean is this and this. Then if the heap is empty, we just set the variable our next option to be undefined, and we break out. Notice if this incremented here, then this will be false right away, because it'll mean we have a next variable that is not undefined, that its value is undefined, and that it is available for decision heuristic. So like this already made sure it was valid when it incremented. This will fail right away. But if this does not fail right away, then it'll grab the minimum off the heap. So it's taking the highest priority variables off the variable heap. And if the variable heap turns out to be empty, then it just sets this to undefined. Then finally, this is a little hard to read, so let's try to help out here. They're saying something like this, right? And then each of these, what they mean is result equals, and each of these, what they mean is like this. And then let's see. So if the next variable is undefined, then we're going to return the literal undefined. Okay. So what we could do is that's already the default, so we could do nothing here. And now we just have an if followed by an else chain. If I put all of this inside of a block like that, it's the same thing. And then if I delete this and invert it, so if our next variable is not undefined, then, so we can see here, now we've clarified something that I didn't know before. We have to pick a variable by this point. This is not going to help us pick the variable. If we got this far and there's no variable selection, then there's no guess. But if we got this far and there is a variable selection, we still need to pick a polarity. So choose polarity based on different polarity modes, global or per variable, right? So user poll, the user preferred polarity of each variable. So user preferred polarity. So I'm going to say, hey, I prefer you to guess this variable in a certain way. And so what we do is we make a literal based on this variable and this assignment, right? Either true or false, right? So if we prefer to guess true, this would come out true. If we prefer to guess false, this expression would come out false. But that's only if the user has a preference. Now, if the user does not have a preference, and we have the random polarity option turned on, then it'll just roll a random double for us and flip a 50-50 coin. If that's not what happens, then it uses the preferred polarity of each variable that is determined by the algorithm. And we don't know how that's getting determined, but that's like already determined by the time we got here. So this heuristic basically boils down to make a random choice, pull something off the heap, and then once we've got a variable trying to do one of those two options, pick a polarity, and that's it. There's nothing else to it. The last one, the CDCL one that we read before, the heuristic they were running here was how frequently does this variable occur? And so they would scan all of the unresolved clauses and count the variables and pick a variable, and they were putting a lot of work into that variable selection. This looks like it's a much faster variable selection process. Now this here is probably doing something similar to that whole work of scanning the clauses and counting the variables, because it's using this order heap, and the order heap is just a data structure that lets you pull things off by highest priority first. So it's probably similar or even the same logic in this chunk here, except that the data structure carries a lot of the magic rather than the code that we see. But that's actually fine. That's just a choice of how to optimize the running time speed of the thing. Okay. And then this part is a little bit less refined. So the CDCL we were looking at was doing a lot of work, even in addition to scanning all the variables, it's also scanning how frequently each variable type, how frequently each polarity occurred, and picking the polarity that's favored um, by the count of the occurrences. Now, the polarity structure here might actually be doing the same thing. So the polarity takes in a variable and outputs a char. These VMAPs are things which take in variables and output whatever you put here. So this is outputting a byte of 1 or -1, or probably 1 or 0 or something like that, from the variable. We don't know much about set polarity. So that just doesn't get used. Set decision variable. Create a new stat variable in the solver. If decision is cleared, variable will not be used as a decision variable. Note, this has effects on the meaning of a satisfiable result. I don't know what effect it has. I mean, I think they're just referring to the fact that... Wait, is this implemented twice? No, this was getting used in new var. Its implementation is... keeping track of how many decision variables there are. And then decision v equals b, insert var. Insert var order. If x is not in the order heap and it's a decision variable, then we insert it into the order heap. Okay, so that's just a little helper for putting it into the decision heap if it's eligible for selection. Okay. Does not seem like the most important thing to wrap inside a function, just saying. But anyway, the yeah, this is just unwrapped. So this is how we cancel decisions. Good. Okay, so let's take a few steps back here. Back to the solver. I want to look at analyze. We've been at this for an hour. I've already done it for an hour. The thing is, I always say I want to do a short stream, but like it takes so long to make some progress on this project, and I kind of get into it. Like I get real. I've gotten past the point of being annoyed, even though I'm perpetually dealing with annoyances. I've gotten to the point of like kind of eating it up again. I'm enjoying the process, and so I'm like, oh, I could go for a few more hours. This isn't a problem. It gets really exciting to think that like the images I have in my head of how I will recreate some of the best ideas here in my style. There are things I won't recreate because they're too far, like they're too much work for what I'm trying to build, and so there'll be ways in which my thing will still be inferior, but there are also ways that I'm like, that's such a cool idea, and when it shows up in my style, here's how I imagine it, and it makes me excited. All right, description, analyze conflict, and produce a reason clause. So the analyze function, we've already seen this in the other CDCL solver. So let me give a quick, like high level overview of what I understand it does. In order to reach this function in the context of a CDCL solver, what we've already done is we've made some guesses and we've propagated deductions about other things that deductions about other variables that need certain values from those guesses. And then we've reached a point where we found a clause where all of the variables in the clause were false. And remember, a clause is a big block of variables ordered together, right? Usually three, but we're just imagine some set of variables that are all stuck together in a big or relationship with each other. And so what that means is one of them has to be true. More of them than one can be true, but we need at least one of the expressions, one of the literals in there to be true. And we need that to happen on every clause. So if we find one of those clauses that is not satisfied, that is in fact all of it completely in conflict, all of its literals evaluate to false, then we are stuck. We've hit a dead end, and we can't solve the whole. We can't satisfy the whole formula based on some guesses and propagations that have happened, without unrolling some of our guesses, or without changing some of the variables we've already set, because this clause has fallen false, right? It's gone into conflict. And so what we're going to do is we're going to look through all the variables implicated in this and all the guesses implicated in this and make some decision about how to backtrack and how to move forward in a slightly different way. And the way we do that is, one, we are going to figure out how many decision levels to unroll in the process of analysis. The other thing we're going to do is we're going to generate a new clause. And what that new clause is essentially going to represent is a new relationship between variables that is not represented in any of the clauses that actually exist in the current problem, but which captures something which must be true in order for the whole formula to be true. So we make this new clause, which it's not necessarily the case that if we make that one clause true, then the whole formula will be true. But it's definitely true that even though this clause is novel and we didn't have it in the problem initially, this clause will have to be true in order for the whole formula to be true. So it does not change whether or not the formula is satisfiable to add that clause into the mix. And it contains information that can guide our heuristics and can guide our solver in different paths. It will cause propagation to work differently. It might cause the heuristics to work differently. And so it is new information, and it is drawn from looking at the relationship of multiple clauses and related to this core conflicting one that we found, right? So you have the core conflicting one that we found, and we're going to go around and gather up information about certain literals that are sort of a part of why we ended up given some guesses that pushed us into this position. We will learn what we need to change. And essentially, another way to put this is we will boil this down into a list of what guesses were initially made independently of each other that can't all be made because of the fact that they cause this conflict. So say I make one guess, and I propagate and I propagate and I propagate, and then I find a conflict. I've only made one guess, right? I started the problem and I made one guess, and I found a conflict. Well, what does that mean? It means that my guess must be the opposite of the correct thing. So once I'm done learning from the conflict, what I should end up with is a clause that tells me, it has one literal in it, and it says that literal that I guessed, I need to guess it the opposite way, right? If I said variable A is true and then it leads to a conflict, then what I should learn from that is that A needs to be false. And that can be represented as a clause that stands by itself that says, A is false, basically. Like, the negation of A is the only thing in that clause. And if I make two guesses, right, the first guess I propagate, no conflicts. So then I look at my heuristic and make a second guess. Propagate, conflict. Now, depending on the structure of that conflict, I might learn one of several different things. I might learn that second guess I made has to be wrong, and that's it. Or I might learn that this pair of guesses is wrong. Now, I can't necessarily learn that this guess by itself is wrong, because if I was going to be able to learn that, I would have learned that off of the first guess, right? So the fact that I made this guess and then this guess means that the two things I can learn are that this guess by itself doesn't work, or that this pair of guesses doesn't work. But either way, I can represent that as a new clause and put it into the game, right? And that new clause will then, what it will effectively do is assure I don't put these pair of guesses together again, right? And that gets more and more complex however far you want to go. If you make 5 guesses and then you get a conflict, you then roll it back and figure out, okay, it's going to implicate the most recent guess for sure, but it might also implicate all 5 or just a couple, some combination, right? Some other subset of the guesses. And then we want to roll back all the guesses that were implicated and make a new guess in light of the new clause that comes out. So the point of the analyze function is to make those 2 determinations. How far back do we roll back? And what's the new clause that we can learn that will avoid this mistake in the future while we're running the solver? That's what the analyze function does. It makes those 2 outputs. So they call that a reason clause. The thing that comes out, the learned clause, is the reason clause, the reason for the conflict. And also the level, we have this concept of decision levels. The decision levels really means guess numbers, guess count, guess indexes. And we're going to roll back to a guess index that unrolls every part of the conflict, not just the latest part, but the whole conflict, right? However far back that has to be. Okay, so let's take a look. I don't know what that means. Let's start there. Outlearned push. It pushes nothing on. Outlearned vec. Let's look at their vector type real quick. What does your push function do? If size equals capacity, then capacity size plus 1. So you think it's just like the null version? Like just put a null in there at position at the end of the vector, as they call it, at the end of the array. Very C++ template. It's always fun, these C++ code bases that don't bother to use the C++ standard template library, but feel it is important to build something exactly like it. Okay, so the trail, just to give you some ideas about what's going on here, the trail is actually a stack of assignments that we have made. And so taking the size of the stack minus 1 is a way of saying the top of the stack, the most recent part of the stack. And so we grab the index for that. Don't know what UIP means. Yes, there should not be an undefined conflict clause. So we grab the clause and we ask, is C, so we're looking at our clause that we're looking at our clause that's in conflict. If C was a learned clause, so each clause has a bit floating around with it, and that bit says, was this initially a part of the problem, or did we learn this one? And so if we learned this one, we bump the activity. We say, pay more attention to this. We're not paying enough attention to this. Then, and that remember there's these heaps that give us priority. So this is, when I say pay more attention to it, what I mean is it more likely to be pulled off the heaps when we say, give me a relevant thing for me to work on. Now, So if P is undefined, we start at 0, otherwise we start at 1. I don't know what P is, but it's a literal that is undefined. And we're going over the clause, possibly skipping the first part. Don't know what that's about. And we're grabbing Q, which is the literal from the clause. Now, seen, I'm not entirely sure what that is. I can kind of guess that it has something to do with, like, it's tracking how allocation overhead, suggestive of C++ caused problems that will not be present, most likely in my own version, I don't think. But the scene variable here gets used in multiple places, so I don't. Is it possible that things are already marked scene when we come in here to do analyze? That would be confusing and weird, right? I'm pretty strongly expecting that if I look around here, I'll find a spot where the scene is getting cleared out. It's getting returned to its initial state. Yeah, here it is. Okay. Okay, let's keep reading. I think that I've cleaned up all of the most confusing structural stuff. Well, let's catch this one while we're at it. Okay, let's read through. I don't know what leaving room for the asserting literal is, but that's what it does. It takes the index, grabs the conflict clause, checks if it's a learned clause, begins iterating, possibly skipping the first one, depending on P, which we don't know the meaning of P yet. And then we take Q out of a literal out of the clause. We check if it has not been seen yet, and that the decision level for that variable is greater than 0. So that what that means is decision level greater than 0 just means that this is a variable whose value has been assigned downstream of a guess. Remember, things with decision level 0 are things which were forced on us by the very structure of the problem. Basically, literals that lived in clauses by themselves had to be a certain value before we made any guesses, and so there's not quite the same logic with them. There's no such thing as like unrolling them or learning that the problem can't be solved because of those, because the problem itself is sort of defined with those in it. But the variables that get their value after level 0 are based on the deduction process of the solver. So we mark this variable as more important to pay attention to. We mark it as seen, so we don't visit it twice during this run of the algorithm. And I think the assumption here is that these things, the scene is always cleared when we get it, and that anyone who uses it is supposed to clear it when they're done with it. It's a little bit unfortunate because we have to just trust there's not some hidden tricks where the scene gets used ahead of time to make this different. I don't think that's what's happening though. But the structure of the code does not prevent that trick from being in play. There's no contract in this code that lets me assume that 100%. But I'm gonna assume it anyway. So then, if the level is greater than the decision level, wait, how would that be possible? Path C. What is path C? I guess greater than or equal to. Can I get oh, path C is local to this function. Imagine that. Okay, so this is a counter relating to the loop in this analyze function. So this is the part where I think I start probably needing to draw a picture of this to fully make sense of it. But if we've not looked at this variable yet, and this variable was made in a decision level greater than 0, we bump the activity, we mark it as seen, and if it was made greater than or equal to the current decision level. So that means, what that should mean is just equal to, right? I don't think it should be possible for a variable to have an assignment from a decision level in the future. And this is where we are in the current time. So this should always be less than or equal to this, I think. But anyway, this is basically saying, hey, if this is a decision downstream, if this is a variable whose value was set downstream of the most recent guess, then increment this counter. Otherwise, put it into the queue of things we've learned. Probably meant to look like that. I might have started breaking this code. Okay, everything's still built. Good. Now, once we've done that, we've added this to the clause. I wanna start drawing this picture. We're adding things to the learned clause if they are from decision levels prior to the current one, and if we find them in the clauses that we iterate over, right? And the clauses that we iterate over start with the conflict clause itself. So the clause of literals where all those literals are false, and any of those that were set, any of those literals who's got their value in a decision before the most recent one goes into the learned clause. And we say, hey, this thing you should know about, this thing you should know about, this thing you should know about, right? But things that were just recently deduced, we don't touch those. We just increment this counter instead. And then, once that's done, we step backwards through all of the things in the trail. So remember, the trail is that stack of variable assignments that we've made, and we're going backwards through the stack, basically unwinding variable assignments one at a time, and we're looking to see if any of them are not seen. So we might have seen some of them here, right? We might have scanned, and as we were scanning, we saw some variables. Some of those variables, we mark all of them as seen. So the things we're looking at now, we're going like go back until we find one that wasn't scanned here. And then we So there's a +1 here because the index gets decremented after it gets used. So whatever index we have initially is the one we... Yeah. So we start with this index here. We haven't used it yet. We haven't used it yet anywhere in here. So we use the top of the stack, and we decrement at the same time. And so the top of the stack then becomes index +1, right? We use the top of the stack and then go down one. If we actually want to use if we want to use that index again that we looked at, that's index +1. So we grab P. P is that one we didn't know what it meant before. P is the thing that has come off the assignment stack. And we look for the reason on the variable P. Now, what is a reason? I think I remember what a reason is, but let me double check. Reasons var P. This might be somewhere I need to go like to the... Are there literals? Where did we define a literal? I don't know. Is it like class lit? Is that somewhere? Is there a class lit? Is it a struct lit? There we go. So the variable of a lit is just the literal without its lowest bit. That's good, that makes sense. The literal the reason on that variable, do we have that here? Reason. Okay, so I think var x is an integer. Yep, there we go. Var and int are the same thing. So the reason on x is stored in the var data. And the var data is... Okay, so it's a map that takes variables to var data. And var data, okay, here we go. So the reason on a var data, the reason of a variable is the clause that we stored with it when we did the make variable data thing, right? And so that happens whenever we assign, right? If I find the assign function, it's around, somehow we make assignments. Unchecked in queue, I think is actually what it's called because of the, yeah. So you can see here, when we make unchecked in queue, we set the var data to this guy here, which means the from clause that we remember and the current decision level. So we remember what point in the decision stack were we in when we set a value for this variable, and what clause did we pair in here as the reason why this variable got set. And we could go and learn more about that by looking at the uses of this function. So when we're adding clauses, if we have lone clauses, we just add the variables from those clauses into the queue of things that need to get assigned. If we... What is this one? Okay, so if we're propagating and we get to the point where we have a critical clause is one where all of the literals are false except for one, which is undetermined. And so then we put it in to the system and say, hey, you need to make this particular literal true. That's where we make those deductions. Here we've resolved a conflict with a learned clause, and if the learned clause has one literal in it, then the only way to satisfy it is to make that one literal true. So we just put it in the system as something that's going to have to work. Whereas if we put later, young Lane, you have a good one too. Whereas if we're making a guess, then we pair the clause with that. So if we are if a clause if we have a clause that's critical and we deduce from that the value for a variable, we attach the reason clause. If we have a guess from a learned clause about one of its variables, we attach the reason clause to the assignment. Okay, here we're making a pure guess from the heuristic. So we run our heuristic and say like, hey, you know, do you want to tell me what I should guess next? And these guesses aren't being forced on us by a clause or anything. They're just guesses, pure guesses. You could think of them at random. You know, it can be randomized or it can be off a heuristic of some kind, but it's just a guess. So those don't get a reason clause. Reason clauses are, again, we're getting them when we have a critical clause during propagation. We're getting reason clauses when we've learned a clause and used one of its own literals to make the guess. Here, I'm not sure what implies is for. I haven't actually seen this getting used a lot or at all. I might need to track down what implies means. So assumptions out. Let's take a quick look and see if implies shows up anywhere interesting. Doesn't look like it. So this is some kind of helper. With no commentary. So I'm going to ignore it. I'm going to completely ignore it. Yep, that works. Okay. JVS Tech, yeah, this is the MiniSat code, and I'm only modifying it in order to help me understand it better. I'm not really trying to contribute or make my own fork of it or anything like that. I'm just trying to learn from the code, and so I'm modifying it to make it make more sense to me, to focus my attention on the issues and pull out its algorithm ideas. I'm gonna sort of write my own in a little bit. We might touch that today. But I want to learn ideas from existing solvers. Yep. Okay. Let's get back to I don't know. I've seen this word lubby or looby around a couple times, and I have not tracked down what that means. Find the finite subsequences that contains index x and the size of that subsequence. I kind of think I get what's happening here, though. This is sort of like the binary tree thing written down a little differently, it looks like. Not sure what it's for, but it's interesting. We will look into that. I think it's probably guiding the heuristic somewhere. Okay, the analyze function. That's what I was in when we went on that. So let's catch up where I'm at now. So we got the we've got the conflict clause comes in. We start processing by looking at the conflict clause itself. Do we change that? Yeah, we change. Okay, so the clause we're going to look at is changing over this do loop, right? It starts with the conflict clause. We scan it. We learn some of the literals from that. Those are the ones that are from earlier decision levels that are members of the clause. And we make sure we don't look at anything twice. Then we scan down the list of the stack of decisions until we find one we haven't looked at yet. We set that to P. We look and see what its reason is. And I guess we're assuming that it has a reason, which is a little bit confusing because some things don't have a reason. I'll have to think that part through. But we're saying, okay, whatever your reason clause is, so a clause attached to this variable that caused us to make this variable what it is, and then we mark that particular variable as being unseen, which I think is redundant. I think this already ensured that. Like, we were going down the stack, we stopped on a variable that was unseen. So this, I think, is redundant, is my guess. And we decrement this counter. So what is the relevance of this counter? The counter starts at 0. If we have a conflict, we have at least one variable in the conflict clause. Yeah, I know. This code, a lot of this code has some readability issues. So, like, if I was gonna rework the code to make it readable on a permanent basis, I would change this. But what this is doing is walking down the stack. Like, here. Oh, wait, this is wrong. I'm reading it wrong. This is while it is not seen. So it's skipping over the things that have not been seen and looking for the things that have been seen, which is super counterintuitive. Okay, so what this does is, let's say that if we have seen this variable before, then break. That's what it's saying, right? If we have seen this variable before, then break. Either way, we also want to do, after using the index, we decrement it once. Stack var, if we've seen it, then we break. Okay, so actually this is not redundant. This makes sense. So that's surprising. It's not scanning for things that it hasn't seen. It's scanning for things that it has. The things that it has seen are the variables that were in that original clause. So it looks down the list of decisions for any places where variables that we just scanned over in the original conflict got touched. And then it's going to visit them again. And how does it visit them again? It sets them to being not seen so that we can look at them again. And also it grabs the reason clause for that variable. And notice it's going down a stack so that it'll find the first one, and it's not as if it is ignoring other equally likely candidates for inspection later in the clause. They're just further down the stack, and we'll get to them later. We look at this new conflict, and we or we look at this new clause that's wrapped up in this conflict, and we decrement this counter. So the thing I want to figure out is, what is the relevance of this? If we saw one variable that was made from the current decision level, then this would go from 0 to 1, and then it would decrement by 1. And we're guaranteed to see at least 1. So this won't ever go to -1 on that pass. But this could go to from 0 to 1, right? And then we find a bunch of other variables that are from previous decisions, and we put them all into the learned clause. And then this is a 0, and it stops. And now look at this. The last thing it does is it takes P and negates it and puts it into the learned clause. So what is P? P is the earliest assignment it can find that was seen. So okay, this is interesting. The first one that comes out of this should be the variable that we deduced most recently, because the variable we deduced most recently will be the one that generated the conflict clause initially. So the first time this runs, it's always taking the top of the stack. In repeats and later iterations, right, of this loop, this then might go looking deeper. But that first variable on the stack must be the one that generated a conflict in the first place, because we find conflicts after assigning a variable and propagating it, and it's during that propagation that we then go, oh hey, this clause here is in conflict, and so we find the conflict right after by iterating the clauses relevant to a particular variable assignment, right? Hopefully that makes sense. So we're expecting that when we do this, we find that P, which was at that decision level, and if that was the only one there, we will then remember it, leave, and store that into the learned clause. But if there were two, so how could there be two? I make a guess, right? Say I'm somewhere into the process. I make a guess about a particular way to assign a particular variable. I make a couple of deductions that are forced by that guess, and after a couple of those deductions, I find a conflict clause. Now it's possible that since I made a couple of deductions, that I set a couple of variables that are all involved in that clause that goes into conflict, right? So the first deduction makes that clause a little closer to false, and another deduction makes that clause a little closer to false, and then the final deduction puts the clause in conflict. But all three of those variables in that case that I just sketched out could show up in the clause that's in conflict from the same decision level, right? Like that's super possible. So in that case, this counter would get bigger, and we would not stop right away. We would then look at all of those variables would come out of this loop here first, right? They're all the ones with the highest decision level. They'll be farthest highest up in the stack. They will come out first, and they will cause us to go and look at other clauses, their conflict clauses, right? Or their reason clauses, the reasons why they're there in the stack. And so those will then give us more information to put into the learned clause, possibly find more variables that are wrapped up inside the chain of deductions that led to the conflict. But eventually, we stop finding variables that were part of. So if I make a guess in 5 deductions, then the biggest this can get is to 5. And once I've iterated through my clause and found all the ones that are reachable by iterating the adjacent clauses, where adjacency is defined in this sort of funny way by variables that are constrained by certain clauses. But iterating through the clauses via their relationships to each variable, we eventually run out of things to iterate when this goes to 0, and so we stop stepping back through the stack, And whichever one we ended up on, whichever one was farthest back in the chain of deductions that was implicated, we put that one into the clause in its first slot. The first slot of the clause gets that one. Then it puts it through a simplification pass. So this part makes sense to me now. And thanks, by the way, to JBS Tech for pointing out how unreadable this was, because that prompted me to actually write it out myself and realize I was reading it wrong. This is very confusing. This is looking for one that we've already seen, was the thing I missed. There's something kind of funny about that I want to think through in another way. Is it possible that we make 5 deductions? The last one is involved in a conflict, and let's say that the fourth one is also involved in the original clause of the first conflict. So when we do this, we'll pop off the most recent variable in the deduction chain, look at its conflict clause, and when we decrement here, this will still be a 1, so we'll go again, because we had 2 of those variables, right? And so then we'll be looking at the clause that caused that deduction. And that variable that caused that deduction, or that clause that caused that deduction, could cause us to see... Okay, I set it up wrong. Say the clause which falls into conflict at the end. It's so subtle. I think that they have to be in order. If deduction number 5 creates the conflict, and the conflict clause contains another variable that also got deduced at the same decision level, is it possible that there are gaps? So deduction 5 and deduction 3 both show up in the clause, but not deduction 4. Well, if it's in conflict now, then it was critical before it went into conflict. And it would have been seen when deduction 3 occurred that this was critical. So deduction 3, could it have generated 2 critical clauses and processed the first one? Is it like breadth first? Is that something I need to understand a little more carefully? Should I think about this like a breadth first walk of the deductions? We're popping them off of we call it a queue. It's a stack, but we are calling it a queue in this case because we process them in this loop in the same order that they go in. So it's a list, and we keep a separate pointer to where how far in that list we want to move ahead. So in that separate pointer scans it like a queue. We also scan it backwards for other purposes. And that's when we think of it like a stack. But yeah, it's like a queue here. And then if we find some critical clauses, we learn how to assign some new variables. We enqueue them here. And then we go to the next clause. So yeah, we end up handling all of the clauses that are tied up with this literal. Before we handle any other literals. So deduction 4 and 5 could both be generated. before deduction 4 gets processed. And then, yeah, this is where I think I just have to start drawing visualizers of these to make more sense of them. Or like developing visualizers of these to make more sense of them. Then the analyze code here scans that clause that's in conflict. Say it finds variable 5 and variable from the variable from deduction 5 and the variable from deduction 3, both in that clause. So it's seen both of them. It's incremented this to 2 twice. It then goes and looks at the conflict clause that fixed variable 5, which was one that was discovered by conflict by deduction 3. And so presumably this clause here will have 5 and 3 in it again, but maybe some other stuff too. But it can't have 4 in it, because if it has 4 in it, then it wouldn't have been able to be critical, since 4 and 5 would both be unassigned in it at the same time. So I think it's sort of like we need to look at the chain of look at it like a tree, where things becoming critical off of another variable deduction creates these like spanning out, and that if something spans out from deduction 3, that if we have deduction 4 and 5 both spanning out from deduction 3, then what we're doing when we find the conflict in deduction 5 is walking back that spanning somehow. That's probably what the picture needs to look like. We can take a minute to draw that in a little bit. What I'm going to do, I'm going to take a short break, and I will be back in about 5 minutes, just so I can stretch my legs, use the bathroom, grab a snack. So I will be back in just a couple minutes. All right, I'll see you guys shortly. All right. Okay, so let's learn about how the simplify part works. Maybe I'll draw a picture of that chain of deductions and the conflict like walk back before we move on, and then I think I want to spend a little time working on the FATSAT solver that's in my code base. Okay. Analyze to clear. What does that mean? I think it's just a local variable. Yeah, okay. So analyze to clear is essentially a local to this function, except that that because of the way that this code base structures its memory management, it apparently was a little faster to keep a copy, like keep the variable in the class, so that it could avoid reallocating it as a local every time. CC min mode, I don't know what that means. Conflict clause minimization mode. Got it. Conflict clause minimization. 0 equals none, so that means there's no minimization. 1 is basic and 2 is deep. Okay. So 2 is deep. What it's doing is a loop over I from 1 to the end of the clause, incrementing I. I'll start with j at 1. So I is always incrementing. J is incrementing sometimes. So we're doing the kind of loop where we have two cursors, a read cursor and a write cursor, and the read cursor is staying ahead, or at least it's never falling behind the write cursor. So it's possible that we read and write to the same spot and advance them together, or it's possible that we read from the spot, don't advance the cursor, and then advance the write cursor, but advance the read cursor. So we read, we don't write, and then we advance. And then when we read, write, and advance together, we're always reading the correct initial input data, and then we're outputting a shortened version of the list in place. So if we look at a variable in the outlearned clause that does not have a reason, then we save it. So reason clauses aren't as interesting as assignments with reason clauses aren't as interesting, and I think that makes sense. We're making these guesses, right? So each guess is like totally out there. Things with reason clauses are deductions off of that. So if I look at a thing with a reason clause, or if I look at a thing with a reason clause, that thing, that variable assignment is based on a guess, a more basic guess. So that's like the deeper reason, if that makes sense. The clause is the causal reason why this particular variable got assigned. But in the system of deductions, or in the system of guesses and deductions, that deduction was only forced because of this guess. So things that are have no reason clause are these more basic guesses that are worth learning. Like, it's worth learning about how those guesses we made were wrong in order to avoid making those guesses again. But another reason to save it is that it is not redundant. So if it has a reason clause, we might still save it if it is not redundant. And that function is interesting. Let's take a look at what that is doing. Not redundant takes in a p, so that's the thing we're checking if it's redundant, which is one of the literals out of the learned clause. So we have this big learned clause we're trying to simplify. We're grabbing a literal out of it and we're asking, is it redundant? How do we check if it's redundant? Well, that's what this does. So I think by redundant we are going to mean that something else in this clause also contains the same information. So if it is redundant, we can remove it. Now, if we have not seen it at all, or if we have seen it, okay, so those are the only two states it should be in if we're doing lit redundant, and that makes sense because we've only assigned zeros and ones to the seen variables so far. Now the reason of this should not be undefined. If the reason for this literal is undefined, then we would have caught it here, so this won't go off in this case, right? It would have been caught by this check. This check here would have found it, and so we would never have gotten this far. So this makes sense too. We only run this on variables who have reason clauses. They're the only ones for which it makes sense to ask if they're redundant. Then we look at the reason clause for the variable. And we're going to use the analyze stack, which is initially empty. We're looping over something, or we're looping starting from 1, and we're looking at the literals inside the reason clause. Checking p parents L. So we grab the literal. I mean, I don't know what else to make of that. We grab the literal. If that is at level 0, or if it is seen in the basic sense, or if it is marked as removable, then we don't consider it any further. It doesn't qualify. So in order to qualify, it has to have a decision level later on. Now, I think probably that, yeah, we're going to notice the redundancy here. So it's interestingly, I think the reason it's starting at 1 is because maybe if something has a reason clause, that it's always the first element of that clause. I'm not entirely sure about that, but I think I'm getting the sense from the structure of stuff in this code that that is a rule that they are following. Okay. So what this might be, when you think about redundancy, if you have a set of things that are redundant with each other, and you look at a pair of them, and then you say, oh, look, these are redundant. You want to make sure not to eliminate the whole pair every time you do that, because say you got like this, and you go like, is this redundant with this? You go, oh yeah, remove both of those. And go, is this redundant with this? Oh yeah, remove both of those. Well, great, you've removed all of the redundant things, and you actually want to leave one of them, right? So instead, what I think is probably happening here is it's going, hey, if we're going to compare against this, even if we are redundant with it, if we've already marked it for removal somehow, then don't do it to me as well, right? So we have to look at two things that are both marked as not removed, and then remove one of them at a time, right? We look at a pair and remove it until eventually we get down to just the one non-redundant instance. Okay, so we look at L. If the L has if L does not have a reason clause, so L is a guess. Or if it's been put into the failed state, which I don't know what that means yet. Then we push onto the stack a 0 and the P. The P is the thing we're trying to check if it's redundant. Don't know what the 0 means yet, but we push onto a stack 0P. We then scan the stack. That's probably the literal that we got from P, just guessing, but I think that's correct because that's a literal. This is being treated as a literal. So if we've seen this as undef, too clear gets the L. L gets marked as failed. So this is saying if anyone from the clause we're looking at is it does not have a reason clause, or if they've already been marked as failed, then we push P onto the stack, scan the stack, and if anything in the stack is marked as it has not been seen, we change those to being failed and push them onto the to clear stack and then return false. That is completely indecipherable to me, whatever that is doing. I've read out step by step. My brain's making no sense out of this. Why would there be a stack that we would push P onto based on whether L was undefined or failed, and why would we scan the whole stack every time we push something on it, rather than just applying this logic to the thing we're pushing newly now? Is it possible that this is changing? But we're never setting things to undef, are we? It's not like things become undef. They start that way. Yeah. So it's not like the states of these things are changing. So what's happening with that stack? We're pushing I onto it. I don't even know when that becomes relevant, because here we're just looking at the literal the whole way through. When does the I become relevant? I becomes 0. P becomes the L we're looking at. C becomes the reason clause for the new P. Okay, so what this is doing is essentially it's hiding it's hiding a recursive stack walk. Okay, so this gets pushed on the stack. We set I to 0 and we continue the loop. So then I gets incremented to 1 and we check again. P is the thing that tells us what literal we're analyzing, basically. And we've changed that to the L we were looking at. Now, in order to get this far, a few things have to be true. L was not marked as removable. It was not seen earlier, and it was based on a decision later. L did have a reason clause, and L is not marked as failed. So in order for it to get that far, L has not been this, this, or this. So L is marked as, L must be has not been seen yet at all. And it doesn't have a reason clause. Then we push P onto the stack. We remember how far into iterating through P we were. So this is like the call stack substitute. We remember I and P for later on the stack, and we iterate in more deeply. Got it. And the reason we're not doing this on the call stack is because at some point we might want to iterate that stack and mark them all as failed. And push them onto the toClear stack and then return that the thing is not redundant. Then if we get to the end of a clause, we do this step instead. And this step says, if we've still marked it as undefined, you can mark it as removable. So it is removable, and we push it on the toClear. And if the stack is empty, then we've actually finished all the processing. We haven't found any reason why to call this not redundant, and so we step out. Otherwise, we restore. We're gonna restore the top of the stack to our local variables. So we grab the I and the L and put them into the I and the P. We restore the clause, and then we pop the stack. Right. So this is saying, hey, get this loop back into the thing lower down on the stack, and then it'll continue from there. It'll go up increment I and run more on the thing that came before. So I don't entirely understand yet the implication of some of this, or even some of this. Like, it's a little confusing, but we're definitely doing a recursive walk through the literals that are associated with reason clauses. So maybe that picture of the deduction chains spanning out and the connections that they form with other clauses through variables will help me. If I had a picture like that, I might be able to then understand what this is doing on top of that picture, right? Like, this is sort of walking through that data structure somehow and doing something inside of it, and I don't have a good mental image of the data structure itself. So that might be something I should do before I try to make more sense of this, is to draw that picture. But let's keep going with where this lived. I think we might need to take some special time to understand that part of the analyze function. But otherwise, if we're doing this deep analysis mode, then we save anything that was a pure guess, and we save anything that is not redundant according to this, whatever this does. And then we put it here. Now, if we're in CC min mode 1, so this is the deep version of the conflict clause minimization. Here's the basic conflict clause minimization. We take I and J, we're iterating I. We look at the variable X. If the variable x has no reason, then we save it, just like up here. Otherwise, we look at the reason clause, we scan the literals of that reason clause, and if any of those literals have not been seen and have a high enough decision level, then we save it for that reason too. So this is like a shallow version of this redundancy check. It's very similar in the sense that it's scanning the literals from the reason clause and saying, hey, if any of them are not seen and they are not from the basic decision level 0, then we can't eliminate them. We have to save them, right? If we haven't seen this, we have to save it, save the variable connected to that clause. If it wasn't made at decision level 0, yeah, for the literal k, same thing, right? That also doesn't make a lot of sense to me. Like, I think there's something about that could make sense, but I'm gonna need a picture just to make sense of the shallow version. So probably the right thing to do is build my picture, make sense of the shallow version, make sense of and then make sense of the deep version. Because I think the deep version makes sense as a deeper optimization of how hard to go minimizing things, based on the same basic principle here. And this is sort of just being less aggressive about looking for ways to minimize the clause. Now let's see. Afterwards, we look at how many we shrink that down, we save that, find the correct backtrack level. So to find the backtrack level, if we learned a variable assignment directly, we go all the way back to 0. Interesting. So it's basically saying if this boils down to we've learned how to assign a variable, so a learned clause with one literal in it, basically saying we now have a proof that this variable needs to be a certain value. So it's saying just roll back all your guesses because there's no point using guesses when we have a proof. Let's start with the thing we've proved and put that on at level 0, and then we'll carry on from there. Making guesses again. But this is like a proof of how to assign a specific variable. So we don't want to guess anymore with this. We want to take it back to the beginning. Okay. And this is looking for the most conservative backtrack, which actually tracks for me. That makes sense. So it's saying, look at everything in the learned clause. This is the list of literals that we're saying, look, you made a situation where all of these were false, and moving forward, one of them has to be true, but we don't necessarily know which one. So we've set it up so that the very first thing in that list is always going to be something, some literal. We don't know necessarily which one, but some literal from the current decision level. So the current decision level is like, we made a guess, we made some deductions. They're all part of the current decision level. Something in there will be the first one. That's the one that's most proximally relevant to where the conflict came from. But the rest is other stuff that had to go wrong for this guess to go wrong, not just this most proximal thing. So we've got all of that in this chain. And what we're going to do is scan through the whole thing, skipping over the first two slots. Or rather, skipping over the first slot and taking the second slot, which is index 1, as the default starting point. Then scanning the rest, doing a comparison, looking for whichever one has the greatest level, greatest decision level. So whichever variable assignment in this clause has the greatest decision level, that sets the backtrack point. We want to go back to there. And let's see. Max I. Okay, so once it's done that, it uses that to pick, like that, the literal associated with that is going to go in slot 1. So slot 0 has that special meaning already of being the one that's most proximal. The one in slot 1 is the second most proximal, right? And then it uses that level as the backtrack level. We clear out all of the things that are in that to clear list. To clear, so something that concerns me about my understanding of this is it doesn't look like it actually clears out all of the scene variables, right? So it's keeping this to clear list. And what's in the to clear list starts off as a copy of what's in the learned clause. And the learned clause does not contain everything that we saw. It contains it contains everything that we saw that was not at the current decision level, plus one of the things that we saw that was at the current decision level. But what about the other things we saw at the current decision level? Do they get marked as seen and they stay marked as seen? Is that for real? Why would we want them to stay marked as seen? It seems wrong. It seems confusing. It's hard to say. But anyway, I think it's time to do a picture. think I've gotten a good idea of the analyze function, an okay idea of the simplification pass. Not a great idea of the simplification pass, but an okay one. And I know what kind of picture I need to get comfortable with in order to make more sense of these algorithms. So I'm going to start with the picture divorced from the algorithm, just to kind of make a sketch of the data structure relevant to all of this. And then we will talk about the algorithm more. Let's see, what color have I got? I'm going to start with this color. Okay. Give me a moment to dedust the screen a little bit on my drawing tablet. Nice clean screen. Okay. So what I think is relevant here is the guesses and the decisions, right? So maybe I want to draw this like this. We have guess, right? And what is associated with a guess? Well, it's a specific literal. So we'll have a guess is actually a literal. I'll write it like this, okay? So there's some literal there. When I say a literal, what I mean is we picked some variable, we picked whether it should be true or false, and we stuck to that. So if I have variable, x100 and I want it to be false, then the literal is the negation of x100. That's what's associated with the guess. And from there, we then start discovering deduction. So a discovered deduction might look like this. We might go, okay, we found a clause. We scan over all of the clauses, let's say, and we find some clauses. So this right here is a clause. Oops. Which enables us to create a new deduction. And the deduction is another literal, right? Oops. Not like that, come on. Right. So the clause gives us the arrow. Let me see if I can do a better version of this. Okay. So we have a guess, which contains a literal. Then we have this arrow, which is associated with a clause, which leads to a deduction. Well, let's do the circle. A deduction, which is another literal. And the guess is like a root, and then this is like a tree, right? So this can be like this. There might be two different deductions that we realize we can make right off of the guess. Now, here are some properties. If I have two deductions off of the same guess node, then these clauses have to be different, because for me to make a deduction, the clause had to be critical. When I made the guess, I scanned my clauses and I find some critical ones. When a clause is critical, there's only one deduction you can make from it. So if this clause was critical and it caused this deduction, it couldn't also cause this deduction, because that would be two different deductions that could be made from the same critical clause. Doesn't happen. But there could be two critical clauses that each make a different deduction. Now, it could also be the case that they make conflicting deductions, and it could also be the case that they cause further deductions, right? So it could be the case that we get to here, and then we go, oh, well, after that deduction, we learn this one. Let me keep doing this in the right order. First, draw the circle, and then write inside of it. Deduction, literal, right? Another one here, circle, deduction. That's a literal. This is a clause. This is a clause, right? So we made a guess. Two clauses went critical. We made two separate deductions. That deduction then causes this and this to go critical. Now, what's possible is that these clauses bear relationships to other deductions, right? So even though we're drawing this as the graph of the tree of deductions, hidden inside this is the possibility that after we process this deduction, this literal here might actually be tied in. Oops. Might actually be tied in with this clause in a sort of hidden back channel, right? It's possible that this had to happen first in order for this clause to be critical. So it's not cleanly separated, right? There are these hidden connections. The strong connections are based on this tree of deductions we've made. But the tree of deductions can also contain things like, hey, for this clause to go critical, it wasn't just that this deduction got us there, but also this deduction had to happen first, and that pushed us towards making this thing critical, right? But that's not a conflict. So a conflict would be if two deductions, right? So hold on, clean up. Oops, I wish that would stay, and then I would take this, and then it's possible that a conflict happens when we come here and this clause is critical. And also, so the conflict could be like this. We deduced when we set this, or how does this actually happen? Let me make sure I write this down in the way it actually happens. Here we are. We process all of the clauses related to this guess first, and that's not going to change. It's not going to later go back and do something based on the changes that happened here and here. This is breadth first. So we go through all the clauses. This happens. So it's possible that things that happen like this might only be, right, I could draw this into, it's possible that this deduction actually made this deduction possible, right? There could be a relationship here like this, where because we deduced that, it's now possible to see that this clause goes critical, and that if you swapped the order, this wouldn't go critical until this had happened, right? But we process all the clauses, and we make a deduction. Maybe we process all the clauses again, and we see that there's another deduction here. Now, once that deduction happens... Okay, what I just said isn't true. If this could not be deduced without the help of this, then this wouldn't have this structure. So we process all the clauses in one pass before we do any, form any deductions. Then what we would see is these two are critical just based on this, right? Then if we looked at this and processed it and put it into the system, that wouldn't affect whether or not this could go critical. because we already had to have this go critical just to get it in this far. If this made anything go critical, that would get built off of this node. Then if we see this deduction here, we process it, we then, after scanning this, we didn't find anything that was critical. After scanning this, so this is where it gets a little confusing. If I say that we, after scanning this, didn't find anything that was critical, the confusing thing about that statement is that this was critical and not processed yet. So how that gets organized is a little confusing. It's like we took certain clauses out of the running because we had already made plans for what to do with them. Based on just this. Now, I don't know if that's true. I don't know if that actually lines up with what happens as the system runs. This is kind of the intuition I have. There could be some reason why this is not actually a correct, useful picture. Let me think by looking at the code for well, we have the picture of propagate up here. We don't need to worry about how to draw propagate because we already know. We have these clauses. Propagate begins by picking a literal, that's the guess, and putting it into the system. And then it gets more literals, and those are deductions. When we put the literal into the system, the process is look at the attached watches and process all of them first. So these all get processed, and possibly new things get enqueued for propagation. Now the things that spot this change in B are things which have put B in one of those first two slots, either as a positive or a negative. I guess specifically things that have put B in there as a positive. All the clauses that have a positive B in one of the first two slots, those get processed in this chain. And they might lead to a deduction. And if they lead to a deduction, that gets put in the queue and processed the same way when it comes out of the queue. Now, I think the code, when it does something like when it's propagating and it does unchecked in queue to assign a deduction into the system, that is immediately giving the variable a value. That's not like later on we'll deal with this. The trail itself gets updated. The map that takes variables to some data about the value and metadata about about when that assignment occurred, that all gets updated right then and there. So it's not like we are saying we'll assign this later. We assign it right away. What's enqueued is that the propagation hasn't happened on that assignment yet. So what's enqueued is that the queue head here hasn't scanned that part of the trail yet, and it will have to finish the propagation work. So it's true that we pop something off and we start iterating the clauses. It's not true all the other stuff that I said. I think we got to take this a few steps back and put in a more detailed picture of how this can happen. So this was true up to here. This is how it works. But then I started getting confused. So what can happen is that after that first deduction, the variable gets assigned, it's queued up that we are going to deal with that deduction. We might keep going and find another clause to process just based on this guess. And we're not worried about the possibility that the clauses that we handled earlier, so say we're looping over some clauses, and some of them gets handled before this deduction gets made, and we're not worried that since we made the deduction, we need to go back and handle those clauses again, because we're going to handle those clauses again when we process that deduction anyway. So anything relevant to that deduction will get found when we process the deduction. We don't need to go back and redo the loop on clauses. But we keep looping on clauses, and we find another one, right? Clause. Here's our circle, deduction, with a literal. And it's possible that this clause, which we found later, contains that literal in it, and that this clause is only critical because we assigned that variable. So it is possible, but it's chained like this. This would be the reason clause, right, for this deduction. And this would be the reason clause for this deduction. But there's a possibility of these things affecting the future, even locally like this, right? And then we might process this deduction and find nothing of interest, or we might find something. So let's imagine that this, oops, that's getting too small now. This finds something interesting, so it makes another deduction. This finds something interesting. So it makes another deduction. And it's possible that what's happening at this point is a conflict gets found. So this required this. We processed this and said, like, oh, based on that, we found this clause, which is critical and connected to the literal that you changed. That's how we noticed the clause was critical. And so we deduced this. And that assigns a certain kind of value for the clause. And then from here, what we are finding, I should say this isn't really a deduction. This is a conflict. So let's draw this like this. We'll back it up. And then we find this, right? It's got a clause, but it is not a deduction. It is a conflict. And it's possible that this clause, right? So this clause, we discovered it was a conflict after we were analyzing things attached to this literal. So this literal went a certain way. It became, it became true, but the negation of that literal became false. And so we scanned clauses where the negation of that literal occurs, and we found this one. And so we said, okay, the negation of this literal in this clause means that this clause might be in danger of being in conflict. Let's take a look. And as we scanned it, we found that it was indeed in conflict. Now, in order for it to get into conflict, without us finding it critical first, something else has to happen. Yes, this deduction made it false, but it wasn't critical here or here. So it had to be something like, in addition to this deduction making the whole thing false, this deduction also contributed or something, right? So like this deduction here set a literal, which is implicated in this clause and made it a little closer to false. This deduction also at the same time set a literal and pushed this one over the edge. And so that's when we got a conflict. So when we get a conflict, it's associated with a clause. And as we scan that clause, the literals inside that clause, what we mean by the fact that it's a conflict is that they're all false. And so then we can go and say, okay, if this clause is a conflict, then all of the literals that are inside of it, so maybe this and this are the two literals that are inside of it that are at this decision level, right? So those two are uniquely interesting to us, but there might be other literals attached to it too. So I want to now go, right? There might be literals. Let me draw that into the picture. We will use a greener color. There might be other literals from previous guesses and deductions living around here that are also helping to push this clause towards conflict, right? So here we have a picture where there are 5 literals tied up with this clause. These 3 are from an earlier decision level. Right? And then these 2 are from the most recent guess level or guess tree. And they're all coming together to make this clause fail to be satisfied. And now what we're going to do is we're going to analyze that conflict and produce a new clause. Okay, so I think a picture like this will help because this will give us an idea of like what a conflict can sort of look like. And now let's read a little bit about the analyze function again and see what it is we're building relative to that picture. Okay, so the algorithm starts by looking at the conflict clause and looking at its key features. It's going to scan the whole clause on the first loop. Afterwards, P is going to become assigned to an actual literal, and then this won't be true, and so it'll skip the P. And we also are saying that we think P, if P is the reason for, if the reason clause, if this is the reason clause of P, then P has been sorted to the front. It's in slot 0. So this is just saying skip over P. If P is undefined, then that means it is a literal that we got in a previous iteration. The clause we're looking at now will have that P in its first slot, and we don't want to scan it again. It's a little weird because we were also marking it as not seen. So that's more confusing than I originally thought. But let's start drawing an algorithm picture over top of that data structure. So it's scanning the literals in the original conflict clause, and I'm going to just kind of draw a timeline of what I think happens in blue. So we're starting off looking here. Here's state number 1. We start here, and we are looking at this clause. We look at each of its literals. Now, there are 5 literals in total. Let me fully color in that orange concept. So the orange concept is connecting literals to the clauses like this. So this literal connects to this clause. Cool. Okay. Now, going from this clause, we're walking back along each of these orange edges. And so we start marking all of these as seen. So this is like a little 1 on it saying, hey, we saw you. 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 And as a result of that, the path counter goes up by 2. And the output learned clause gathers up all of those things which are from earlier guess trees, right? So if we write down over here what's happening in like a list at step 1, what's happening is we process clause 1. Afterwards, path counter has a value of 2. And let's go through here real quick and put down some names on these things. I didn't do that before, so we'll call these X, Y, and Z. And I'll call the other ones A, B, C, D. Okay. So path counter is 2, and our learned clause looks like X, Y, Z. Right? So there's step 1. Now, after that, path counter is 2, so we're going to actually look at the most recent decision in the trail, set P there, update the conflict pointer, set P to not being seen, and decrement path C by 1. So then when we increment, or when we iterate forward, the most recent one, given the story I was telling you, this happened, this happened. This happened. I think I did this in the wrong order. If this happened and then we found this, that affects that. We kept processing this and then this happened. We would have processed this before this. So it makes a little bit of a problem here. The conflict should have been discovered here, and yeah, this would have discovered the conflict. This would have made the deduction, because process that. We enqueue this, we process this,
No, this is fine. So what's happened is this deduction would not have gotten processed yet, but the value, so we would not have done, this wouldn't have gone through the enqueuing, but the deduction happens, right? We make a guess, we see the clause that gets critical, and we make a deduction, and we enqueue to later chain out from there. So the chain out from there hasn't happened yet, but the deduction has. So we did here, deduce, deduce, deduce and enqueue this, deduce and enqueue this, pop this from the queue, deduce this and enqueue it, pop this from the queue, and then find the clause. This here was deduced. It has not gone through propagation yet, but it's not going to because we found a conflict here anyways. And so we are now resolving that conflict. And the deduction gets assigned right away, even if we don't process the propagation until later. So this is where the conflict would come from in this picture. And yet this would be the first thing we would find, right? When we walk backwards through this trail, we're going to find two different literals, both attached onto this clause, right? That are at this, they're part of this guess tree that is active, right? This guess tree is the most recent one. Two literals will qualify. That's why path count comes out as 2 over here. And we learned X, Y, and Z since they're from earlier guess trees. Sorry, just getting a little interested in making it look nice so I can follow it without getting distracted moving forward. Okay, so these ones from earlier guess trees go into here. Then we iterate to one of these, we iterate to another clause. And how do we do that? Well, we look through the decision stack, and the decision stack is going to have this at the top. This was the last assignment that we made, the most recent assignment that we made before we found the conflict. And so that's the first one we will find. Since here's how it's working. We are looking specifically at ones that got seen. So when we went tick, 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 tick and looked at all of these, they all got seen. So these are the only ones in the stack that are eligible. If there had been other deductions that weren't relevant to this clause, that would be fine because they would not get marked as seen, and so we wouldn't have to think about them anyways. We're ticking backwards through the stack to find the first deduction in the stack that has been seen, right? And then we take this one, because that'll be the one that's most recent, and we look at this clause. So this becomes the focal point of iteration number 2. Okay? And now it's possible, this is where things start to get interesting, that more literals will be tied in with that over here. So let's open up this picture. Say, hey, there are even more interesting literals involved in this story. Alpha and beta. And they are connected into this other clause over here. So I'm going to draw a picture like this. right? So those there are connected into this clause as well. There are from earlier guesses as well. And then we iterate all of those. Now, as we're iterating them, we marked this one is not seen. So we can mark it again in this iteration. It gets seen in iteration number 2. Oops. I don't know what that just did. There we go. So it shows up in iteration 2. This one over here shows up in iteration 2. And those two show up in iteration 2 as being seen. And we find that the path count's going to go up again. So the path count in the transition from 1 to 2, the path count drops back down. So let's do this. We've got this arrow, path counter is a 1, which means we keep going. And now we're in stage 2. Afterwards, path count will be 2 again, because we're going to get well, hold on. We increment it here and here, don't we? So the path counter becomes a 3, I think. Let me double check that, but I think that's right. So it was a 2. It gets decremented here at the end of the loop, so it becomes a 1. It then gets incremented when we see the first decision variable that the p that we pulled out gets seen, and possibly another one. So yeah, it gets incremented twice again, and it goes up to 3. And let's see, that one and that one get ignored, but these two, these two here, both get pushed into the learned list like this. So this becomes X, Y, Z, alpha, beta, X, Y, Z, alpha, beta, and there is our second iteration of the loop. We move forward, path counter becomes a 2. And we move on to step 3. So where would step 3 take us? Well, it would keep going down the stack, and it would find that this was the next thing in the stack that it has marked as seen. So it would then look at the reason clause there and take us to this one. Right? So let's say that this is actually the full totality of this clause. This clause doesn't have anything from over here tied in with it. It just had this literal, and this literal. So when we made this guess, it caused this deduction for reasons we don't know yet, because there's not enough clauses attached, or there's not enough literals attached to that clause to totally make sense of it. I mean, maybe this was a clause of 2 elements. We made this guess, causes this deduction. Those 2 literals being fixed causes this deduction. This deduction causes this one, which is tied in with variables that were set earlier, which causes this conflict tied in with variables that were set earlier. We've gathered up all those variables from earlier concepts, and we've looked at this clause, and this clause. We're really just iterating back through all those clauses that were involved in the most recent decision, or guess tree still. Now from 3, this one here will have been marked as not seen to get this far. So this will get another mark. It's seen again in iteration 3. This one won't get another mark because even though it's connected to 3, it's already been seen and it hasn't been marked as unseen. It becomes marked as unseen if we pull it off the stack. The one we pulled off the stack is this one. So this doesn't get seen during 3. It just gets skipped. Now, this one gets seen during 3. And since none of these, so that means we increment once, twice, but not 3 times. The path counter doesn't get incremented if we don't visit something with that little subscript. So we get 1, 2 of those, and we don't get any new literals into the learned. So that's what that iteration would look like in this picture. So the path counter went up 1. Well, it went up 2, didn't it? We saw this and we saw this. Here we saw that and that went up 2. Here we saw that and that went up 2. Here we saw that and that went up 2. So the path counter goes to 4. The learned goes to what it had before. X, Y, Z, alpha, beta. Okay. And then we have figured out what happens on iteration 3. The path counter goes down again. And now it can only ever stay the same and go down. It can stay the same because we're still going to be popping these literals off the stack and then marking them as unseen and revisiting them. So we still get a chance to pop this off and revisit it. We still get a chance to pop this off. But that seems like it would be a problem. So I got to think about what that would mean. That's a little confusing to me. Yeah, that seems off. So anyway, let's take a look at what happens in step 4 here, given how well I understand this. Also, we got to keep in mind it's possible that I've reconstructed the meaning of the algorithm in my head the wrong way. And so what I'm playing out in this picture might totally be wrong. That's kind of what we're exploring to find out. So we finished with this clause. We looked down the stack and found D. We looked down the stack and found C. And then we looked down the stack and found B. That's the next one, right? So 4 will be looking at this clause. This will get marked again during 4. So that'll go up by 1. And notice if we had, like, if any of these literals here were tied in over here, they wouldn't get duplicated here because they're marked as seen. So again, things only go here if they're new. We don't get duplicates from these earlier guest trees showing up. But anyway, so 4 looks at this clause and says, okay, this is new, so that'll increment the path counter by 1. This we've already seen, and it only means this is new because when we pop something off the stack to iterate it, we mark it as unseen again. So this goes through again, gets marked as seen. This, nothing happens, and we stop there. So all that would happen here is the path counter stays at 4 for a little longer. Learned stays identical to what it was before. And the tablet has, there we go, lost focus or something for a moment. X, Y, Z, alpha, beta. All right, so then it's going to look further down the stack and it's going to find this. And this is where I think I must have a bug in my understanding, because it's going to look farther down the stack. Keep in mind, it's looking for things that have been seen, right? While this is not seen, keep looping. It then takes the thing we found and takes its reason clause. This is a guess. It will not have a reason clause, so that will become undefined. It marks this as not seen, and then it decrements. So the decrement here would take us to path counter equals 3, but not enough to exit the loop. Then it would come to the top, and it would assert. Okay? So that's why I think I did something wrong. Oh, and you see what I did wrong here? You see what I did wrong? I forgot that we skip over P. Okay. So let's roll back all of this. We'll fix some of the picture, but I want to roll back all of the blue. The blue didn't happen the right way. Oh, this is sad. A lot of it had to go. Okay, let's fix this picture to have all the features again that I want. So, there we go. Mark these like this: V, W, X, Y, Z. Like that. It's an easier way to do bold here on Milton. So zoom out, and your line gets a little thicker. There's also brush size. You could always just touch the brush size. And if you don't lose the window focus while you're at it, you get a nice clean thick line like that. Like that. There we go. Looking good. And then tying in the literals to their relevant clauses everywhere. So the literals that point to deductions also have to be relevant to the clauses that they made critical. Or that they made conflict. The literals that are found in deductions have to be related to the reason clauses. And let's see, we go boom and then boom, boom. Yeah, so then we wanted something like a connection from here over to here. And let's change it up a little bit from what I did before and make it a connection from here up to here, just to make it more interesting. A little bit of new flavor to give us something to be excited to see how it plays out now that we iterate this again, try to follow the rules correctly again. Here we go. Step one occurs right here, looking at this clause. We mark all of these as seen because this was the conflict clause. We don't have any literal that we are examining up close at this stage. Okay? Oops, those don't get seen. Those are connected to other clauses. But yeah, those 5 literals get seen. Those 2 cause the path counter to increment. So we have a path count of 2 and learned XYZ. So here is our step number 1. Path C equals 2. Learned equals X, Y, Z. X, Y, Z. Boom, boom, boom. Boom. Then we step down. Path C gets decremented every time we step down. And we are on to step 2 because path C didn't go to 0. So we take a look and we go, all right, look down the stack. Here's the most recent thing. Oh, I forgot to add drats. I should have put this in before I started doing blue. We'll lose it again if I have to back up, but it's fine. It's a lot less to lose than last time. A, B, C, D. Okay. So D was the most recent in the stack. It's the most recent assignment that we made. So we find it first, and since it was seen, it doesn't get skipped. We mark it as not seen, so we'll put a little underline underneath that to say that that got undone. And then we start iterating over this clause for step 2. So step 2 is looking at this clause. And what happens? Well, it skips this one because this was, since this deduction has this as the reason clause, our interpretation of all the code in the code base, although we haven't proved it, the structure appears to be that if I have a deduction clause, if I am a variable and I have an assigned deduction clause, or if I am a variable that is assigned and I have a reason clause that goes along with my assignment, I have a reason clause sitting next to me, right? Then I came from a deduction like this, and that clause will have me sorted to its first slot. It's sorted to the front. And therefore the loop now skips me in the code. And so the 2 iterates through all the things that are connected to it. So that gets skipped. This does not get skipped, so it gets marked. Path C will go up by 1. The path counter goes up by 1. This gets marked as seen at this point. So path C is now a 2. And the learned array becomes x, y, z, w. W gets added to the mix. X, Y, Z, W. Okay. There's my step 2. Now let's see what happens. So at the end of the loop, path C gets decremented. It's not 0, so we have another step. So it looks down the stack. The next thing it finds is C. C is marked as seen, and it is marked as and it is the most recent, right? It is marked as seen, and it is the next most recent assignment in the stack. So we take that one and we go, all right, you're up. You your deduction clause, or your reason clause, the critical clause that created this assignment, is now our focus. And also, you get marked as unseen again. Now from here, we iterate out, and we look at all of the attached literals. We don't look at this one because, again, we're skipping the literal that is right on the deduction from the clause. We are skipping this one because it's still marked as seen. Okay, I want to stop and point out an important pattern that I've just noticed. So I started getting worried about, like, yes, this run through the algorithm might work. Looks like it might work. But I got worried about an idea that, like, what if these things which we're marking as unseen, like this one and this one, are going to start incrementing that path counter. So, like, if this literal had an orange arrow that went from there to this clause, then here we would finally see it again, mark it as a 3 and put 3 there. So we would see this and this on step 3 of this loop and increment the path counter twice. And that would give us enough time to find our way back to this one. And again, if we pop this one off the stack, something has gone wrong. But that can't actually happen. And the reason that can't happen is that these orange arrows coming into a clause, they are quite constrained. The only orange arrow that can come into a clause that's sort of from the future is the one immediately from the thing it deduces, right? When we see a clause, if it caused a deduction, the only variable or the only literal in that clause that was not fixed when we made that deduction is the one that lives on the end of the deduction arrow, right? This guy here is the only literal that was not fixed. Everything else had to come from earlier, either earlier steps in the iteration of the same propagation phase or from earlier propagation passes, right? One way or the other, they come from farther down in the tree. Things that we mark as unseen, things that we unmark here, I don't think they can ever show up again. I don't think they can get revisited. I don't think that's possible. And the reason I don't think that's possible is they get skipped when they are first seen, and there can't be this after decisions that happened or assignments that happened earlier than this can't be dependent on this literal, because this literal's only come into existence here. It only can be depended on by later deductions, right? Now, there's no clause here, so it's possible there are clauses that are affected by this deduction that are in play in the future, arbitrarily far. And it's also possible that this deduction affects clauses immediately into a conflict state. But it can't be the case that this deduction affects any clauses that happen earlier in time in the deduction tree, because those clauses only they only become critical if all of their literals are set. Right? So these arrows can't flow backwards in time very far. They can only flow backwards to that one clause that creates them in the first place. Okay, so here we are looking at iteration 3, this clause. This one we skip because it's the one connected to the clause deduction. This one we skip because it's already marked as seen. This one gets seen. And so we increment path counter by 1 because that's at the correct guess. That's at the correct level. It's a part of this guess tree, so it increments the path counter. And we don't learn anything. Now, my concern is we've popped this and this. We have 2 more things to pop, and our path C looks like a 2 right now, but I think it's going to decrement once. And if it does not increment at all, we'll be fine. Right? So we popped this one, we popped this one. B is up next. So here is step number 4. And when we popped this one, we marked it as unseen. Now we skipped this one in the iteration. We skipped this one because it's already marked as seen. And so we end up only visiting this one for the first time. This is the only one that gets marked as seen from this pass. Okay. And so path C did not get incremented, so it stays at 1. And the new list of literals in the learned clause looks like this. X, Y, Z, W, V. Right now we've got all of them in there. Boom, 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 boom. Now what happens is we get some new behavior because we come down here and path C equals 0, so we enter into the end of the collection out stage. Here, what we do, we pop off this we pop off this. This is the next one on the stack. So we popped this, popped this, popped this. This is the next assignment in the stack. And we pop it, but we get this undefined conflict. We get an undefined clause since it doesn't have a reason clause. We mark it as unseen, so that hasn't been seen now. And we decrement this, giving us that 0, which gets us out of the loop. And then we put P, which we just grabbed, which is this guy, this literal here, the literal called A. We put its negation into the learned clause at the very beginning. So what we have at the end is a learned clause that looks like this. Oops, give me window focus. Window focus, please. There we go. X, Y, Z, W, V. Boom, 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 boom. Okay. So that's what it produces when we don't also count the simplification pass that happens next, right? We had a guess, ran some propagation, making these deductions, setting up reason clauses with each other and stuff like that. Found a conflict where we were propagating the consequences of setting this value, and found a clause that couldn't be set true, and it couldn't be set true after the fact that this and this had both been sort of pinched on it at the same time. Then what happens is it looks at these clauses kind of going backwards in the order of what deductions were made. Boom, 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 boom. And it never sees any of these twice. It can see one and mark it as unseen, but it won't count that again. So at most, what happens is this clause is 1, 2, 3, 4. There are 4 variables set, and there were 4 deduction clauses. 3 deduction clauses and a conflict clause involved. So we end up with this counter hitting 0 right when we got back here. Now, it wouldn't necessarily have to be that way. I could add more deductions that weren't tied in to the picture without changing anything, right? There could be irrelevant deductions, and then the path counter would still reach 0 here, even though there were even more deductions. But the point is, it can never go past this, now that we understand that it only sees these once, ever, right? In fact, it only ever sees anything once. It's just that it leaves the ones that it pops off the stack, it marks them as back as being unseen, which might be relevant for the next phase. I think that might be the case. So it then puts the last thing it pops, whatever the most root thing is in the tree, which may not even get all the way back to the guess, I don't think. It doesn't necessarily have to, but it can. It finds the most root thing that it found during this iteration backwards, and puts that at the beginning of the learned list, along with all of the relevant literals from outside of this guess tree, from earlier guesses that were made. Puts them together and says, okay, in order to make the original conflict, all of these things were false. Like, having all of these things be false was necessary. The ones that are tied in directly are necessary for an obvious reason. If one of those was true, this wouldn't have been in conflict. But these other ones are also relevant. Why are they relevant? Because they helped to make the criticalness of the clauses. So as we're going back through these recent clause deductions, all the things that show up in those clauses, besides the one true thing, right? The deduction was the thing that saved this clause, made it true. Everything that's flowing into that clause was making that clause false, was a false piece in that clause. And so all of those things get put together as saying, hey, if we have all of these things being false at the same time, it seems to create a problem. We were learning that if you make this false, this false, this false, this false, and this false, and then you make this true, right? I have to actually mark that correctly. I didn't mark that. We put the negation of A right there. If you make all of these false and you make this thing true, well, it leads to this conflict. So what we've learned is that you can't have... Well, let me double check something. Right, okay. We've learned that you have to make one of these things true. You can't have all of these being false at the same time. So these were all originally false, right? X, Y, Z, W, V. These were false. A is true, but the not A is therefore false. And so we're in a situation where all of these things are false, and that's unbearable. It creates a conflict, right? And so we've gathered up this new idea that wasn't in the original problem, but that reflects the reason why this conflict occurred. And it reflects it by saying, hey, you have to make one of these things true. And so the reason this conflict occurred is that all of these were false. This occurred because all of these literals came out false. And so now that we know that, we know we have to make one of them true. Okay. But then it runs through a simplification pass. And that's the second part. So let's label this. This up here is the analyze part. And then there's a simplification part. We'll look at the basic version of simplification first. Now, simplification starts from this thing we've learned and reduces it. It minimizes the size using this logic here. So this is just a loop with a read pointer and a write pointer iterating across this. It starts from 1, so it doesn't... The yellow literal there is off the table. That one has to be in there at the very beginning. Starting from the literals that came from outside of this guess tree, it's got a read pointer and a write pointer. And it's going to try to eliminate some of them. But the ones it keeps are any of them that had no reason. So remember, a reason is a deduction. So if any of the literals we have were just guesses, then we can't eliminate them because there's no way, we don't have any information about where that, how to simplify or relate that knowledge to other things, right? It's not like we can look at this and go, oh, well, this was only true because of the fact that we guessed this. It was sort of narrowed in on us this way. No, we just guessed it. We guessed it out of nowhere. And so whatever we learn, we don't have any way to break down knowledge about guesses, right? Or we don't know how to break down any knowledge from a literal that came from a guess. So we just have to keep that. And then it's saying, otherwise, look at the reason clause and look through all of its literals. Again, since this is a reason clause, we skip the first slot of the clause. That's the same thing as saying skip X, right? X is going to show up. If X has been assigned from a guess, we catch it here. If X was not assigned from a guess, it has a reason, and it is the first literal in that clause, so we can skip it by just starting at 1. So we look at all the other literals in the clause, and we find that if all of them are seen, which means all of them have been marked here, right? For instance, if I'm looking at this and it is a reason clause, and that reason clause is made up entirely of literals from over here, right? If the reason this is the way it is because of this and this, well, then this is a little bit redundant, right? Having all of these together gives us just as much information as having just these two, because these two implied this anyway. So if this and this implies this,
then instead of saying this and this all need to be a part of the what we learned, we just say this and this should be a part of what we learned. And we also require that the level be greater than 0. So to keep if we haven't seen it, so here's the other trick. If I'm looking at this, if I'm looking at this and it's got this and a third thing in its reason clause, right? So this guy has a reason clause, we're saying. X has a reason clause. Y appears in the reason clause. Z appears in the reason clause. And some other thing, alpha. But alpha was assigned at decision level 0. Decision level 0 is special because we can't do anything to change things that happen at decision level 0. Those aren't up to us. So if we find something which is simultaneously not something we've seen before, and it is not something that was chosen at decision level 0, then we keep the literal that we got from that, because there's something about that literal that cannot be deduced. There's something about why that literal is set that cannot be deduced from everything else that we already have, right? So everything marked seen that we see here is in this learned clause. If this has a reason that entirely contains things that are already here, and things we can't change anyways, then it's redundant. Because it doesn't tell us anything that we don't learn. It doesn't tell us anything about why this conflict happened that is unique. It doesn't tell us anything that we can't deduce from other parts, right? And so that is the logic of the basic simplification. So in this case, for instance, in order to run this, we would need to have a little bit of a picture of how X, Y, Z, W, and V relate to each other. And we'll say that W, we'll draw the picture like this. So X is going to be up here in a deduction. With Y and Z hanging out like this. And it's going to have those little arrows. So its deduction clause, its reason clause would look like this. Okay? There's that clause on X. Let me go like this. Clause. So we've got another guess tree here. I've done it in green instead of yellow because it's from an earlier guess tree. But X got set after Y was a guess. Z got deduced from Y and maybe some other stuff. But then X got deduced just from Y and Z. And so if we have that structure, what we're saying is X had to be true because Y and Z push this clause towards being false. And so if you want to learn something and then simplify, saying that you can't have all of these together is the same thing as saying you can't have all of these together, right? If I can't have negative A with X, Y, and Z, then I can't have negative A with Y and Z, because Y and Z implies X. Does this make sense? Hopefully. So when I say you can't have them, if Y is false and Z is false, then X has to be a certain. Then the X has to be false. That's what we know here, right? That's what we know here. If Y is false and Z is false, then that forces us to deduce the literal X.
this value for y, this value for z enforces this value for x. That value for y and that value for z enforces this value of x. So putting them all together here and saying that this value, and this value are all false together. When this literal and this literal are both false, this one has to be false already, is essentially the issue, right? That's why it's not interesting to keep it. So we'll keep this as a little bit of extra picture. And then the simplification process goes like this. We start with an I and a J looking like, let's start writing this just in blue. A, X, Y, Z, W. Actually, I'm going to draw the picture a little differently now. Boom, boom, boom. Well, let me draw it like this. A naught divider X divider Y divider Z divider W divider V. And we start off with, this will be like our read pointer, right? So we have a read value here. And then we're writing all of these things out. So we have an out. This is like the in, and this is like the out. I'm drawing them as separate, even though it can be done in place. So this starts with an A naught built in, and then we've got 1, 2, 3, 4, 5 spaces to fill up, right? And so we have a out pointer right here. And then what we do is we go we ask, is X redundant, right? So it's like this. Is redundant X? And that leads to, we go, let's see, this is step 1. And we go over here. We look at this reason clause here. This is the one we're interested in. And we find that Y is in the learned list, and that Z is in the learned list, right? We're looking at the things inside that clause. Each of them is already inside the learned list. And so the reason X had to be the way it was because of these things that we're also already looking at. And I just double check that I've understood correctly. Yeah, when we say scene, we just talk about the variable because it only has one assignment at this point. Okay. Y and Z are both part of that clause. But Y and Z are the other parts of that clause, and they're already a part of what we've learned. So then we get the answer from that pass that says yes. And so then we just go on to step 2 without taking X. Right? Now 2, we line up the the read and write pointers again. So 2, we have the right pointer looking right here at the Y. Z, W, V. And the out pointers are right here. And so now we are asking, is redundant Y question mark? And that has us looking at that just goes straight to no, or that just goes straight to no. The reason that goes straight to no is because Y is a guess. And we could write that in there as the explanation, right? We go, Y is a guess. Therefore, no. And so then that leads to write Y. And so we then get, right, here's the input. So at step 3, our picture can look like this. A, X, Y, read pointer, Z, W, V. Our output can look like A bar, Y, right pointer, empty cell, empty cell, empty cell. And so now we ask, is redundant Z? Now, in the case of Z, Z is not a guess. So if we draw this picture a little more carefully, right, we have Z is deduced from this, Y is pushed on this. Let's say that there's just something from somewhere else also pushed on this. And let's say that it's not one of these. If it was one of these, I would need to know that because then it would show up as being inside of learned. But in this case, the thing that made this clause go critical has not been sort of sucked up into the clause that we learned. And so what we find then is as we're trying to process this, we go, okay, well, is Z redundant? Well, we look at that clause now, right? So we're now, here's number 3. We look at this clause and we ask, is Y learned? And it is. It's a part of the learned set. Let's set that the name of this variable over here can be something like alpha. and we say, hey, look at this. Alpha is not learned. So there's our computation, and that leads to no, which leads to write Z. Okay. I think that makes sense, right? And it would go on from there. It would do steps 4 and 5, but I'll just sort of, fill that in. Like, here we go. We get to the end of that algorithm. And so we have the analysis pass is drawn right here. The simplification pass is drawn right here. Okay. So this key idea is that we're asking, is this redundant information? And the information is redundant if it is not a guess, and it's not redundant if it has a reason and everything inside that reason is already contained inside of what we've learned. That's the basic idea. Now, the more advanced one, I think, digs a little deeper. I think that's what the difference is. I think what this one is doing is probably saying something like, okay, maybe some of the reasons for this variable are not, some of the immediate reasons for this variable are not things that you've learned. But maybe if we dig deeper, what we're checking is, but did the things that we haven't learned, did they have a reason? And were those reasons things we have learned? So we immediately know it's not redundant as soon as we find a guess or if we find something that failed. We mark something as once we know something has failed, we know it's failed forever because it's a variable. So we're kind of like in the whole set of variables. They can either be, we're not sure if they work or not, we're sure that they're redundant, or we are sure that you cannot remove them, right? Now, what I think is happening is we're iterating the clause like we normally would, and we're saying we're iterating the clause like we do in the basic case, and we are ignoring any literals in those clauses that are level 0 because they don't contribute to anything. We're ignoring anything that we've already marked as removable. Now, I'm not sure what that corresponds to, but it's sort of like it's preventing us from hitting false. So it's yeah, these are things that if they're true, then this literal can be ignored because, well, in this case, it can be ignored because it's just a basic fact, right? It's like, it's basic fact that we're not going to be able to change anyways. Learning about it doesn't change anything. This just means we've already seen. So this compares to the basic version that we were looking at a minute ago. So if we compare them side by side a little more, instead of doing it in our heads, redundant. Yeah. So this version looks across the clause, they both skip the first part, which is again confirming my hypothesis that a reason clause or a from clause, a clause that went critical and created a deduction always puts its deduction in slot 0. Then we loop over the rest of the clause. Anything that was a guess, we just take it as is. Anything that had a reason. So here, we're doing something a little different, right? No, this is the same. We're saying if it was a guess, we keep it. Then we check for redundancy. This is the check for redundancy here. This is the check for redundancy here. If we find a reason why so this is like saying it's not redundant when we find a variable that we haven't seen and isn't a basic fact. This is saying it's not redundant. So this is a variable that's not a basic fact. We haven't seen it, and we haven't marked it as removable. If it was marked as removable, I think that's just a subset of things that we've seen, probably. Because we're not going to be interested in removing things we didn't add. So the things that we've seen are the things that can become removable. And thinking about it here, I don't think that any of these can... Okay, I think the marking unseen probably threw me for a loop way more than it needed to. So here's what I think is happening. Let me show you. Here during analyze, it does this annoying thing of marking them as unseen, and that caused me to earlier run the whole loop in my head out when I was drawing it wrong and thinking that I could revisit them. But I can't. The algorithm is set up to make sure that that doesn't happen accidentally. It's just helping to clear out the scene map. So anything that gets set does in fact get zeroed out. It's just kind of like by a trick. It gets zeroed out here if we popped it off the stack, right? If we didn't pop it off the stack, then it ends up inside the learned clause here or inside the learned clause here. The thing that got popped off the stack, the things that got visited here that didn't get popped off the stack are the only possible exception, I guess. So I don't know. Is it possible? Well, however many of these you see, it keep iterating. So I think if you see one of these things, it's pretty much guaranteed that you're gonna see it, because we're counting how many of these orange arrows we see. Those orange arrows correspond to these orange arrows from yellow deductions correspond to recent things that are on the stack that we're gonna pop off. One of them has to, and that'll have, that can't come from that, so it's got to come from farther back. Right. Yeah, so I think it's pretty much guaranteed that the things that don't end up here are getting zeroed out here, and then we're keeping a list of the things to zero out. All of this just to be able to say, clear this to 0, without having to clear it to 0 in like a MemSet for some reason. Maybe it's way more efficient to only clear out the couple of spots that you marked, and it's worth all that extra effort. I'm not sure. Anyway, that makes more sense now. Either way, whether it's necessary for efficiency to do it this way or if it's just a strange choice, it's a little confusing, but this is a part of clearing out the map. I don't think that any of these things
can be influenced by this, and I'll tell you why I say that. First of all, the literals that come in here are things that are in the learned clause past the first spot. So these are all things that are from before the current guess tree. And second, when we take one of this literal P, we look at its reason clause. Its reason clause means the clause that was critical that created a deduction to set this variable. Now, since this was from a guess tree earlier than the current one, everything contributing to the criticalness of that clause must have also been set in guess trees previous to the current one. So as this iterates these L's are also all going to be ones that weren't cleared to 0 here. If it's marked as unseen, then we've literally not seen it. It's not like we saw it and then unmarked it. These unmarks can't show up here. If we haven't seen it, so if we've seen it already, then as we're scanning these are the literals inside the reason clause that aren't P. So we're looking to see any of them that are ground level 0 don't change anything. If they're seen, that means they are inside of the set of learned literals or variables, right? They're inside the learned clause already. If they're removable is just a subset. While we're running this algorithm, some of the things that we've marked as seen, we change them to being marked as removable. So to become removable, you are also seen already, okay? And so these are basically saying the same thing. In this case, they're both saying if we've seen this thing. There's two different ways two different states it might be in if that statement is true at this point. So if it is seen, this literal doesn't change anything for us. But if we find a literal who is a guess inside that clause, then, or if we find a variable that's already been marked as failed, one that is not possible to, the one failed means it's not redundant. It cannot be removed. So when it says failed, what it really means is non-redundant. This is redundant, confirmed non-redundant. So if it is confirmed non-redundant, when we find it, here, we're saying that makes P, which has it as a reason, non-redundant as well. That seems wrong. I must be interpreting this a little off. Because if it's confirmed non-redundant, that doesn't mean that things deduced from it are necessarily non-redundant, right? L might be non-redundant, but that doesn't mean that P, which was deduced from L, is not redundant, because the fact that it's deduced from L might very well be the fact we're looking for that shows it is redundant. So I'm not sure if that's quite right. But if L is undefined, that means, or if the reason for L is undefined, that means L was a guess. That makes a little more sense. That lines up with what we saw here, right? We looked at the reason clause. We iterated the literals that hang out with that reason. Any of them that are not seen. Okay, yeah, I think that this here means we can't break L down. There's no way to break L down because if we've gotten this far, then we know it wasn't seen and we know it wasn't this. So we could just say, looks like we've got a variable here that is not accounted for, right? Returning false
from this, man, this is confusing to decode. Returning false from this lines up with doing this. So here we're saying if we are looking at a variable, right, if we wanted to, we could reinterpret. Let me rearrange my desk here since I'm not drawing anymore. We could rearrange this code a little bit to dramatically enhance its readability. Are you ready? What we're going to do is a couple steps. First, we're going to put a negation here. And then instead of doing a continue here, so what is this continue actually leading us to right now? Right now, when that continue happens, none of this happens, none of this happens, and nothing happens down here. Okay, so this continue means we skip this. So if I negate the condition, which I did, and put the if around this, and then I can start pushing that not into the system. So level is greater than or equal to 0. So if it's not 0, that's greater than 0, and not this. So then we can say not scene source and not scene removable. Okay. So now we can see that this and this look very similar, right? This is using not seen, whereas this is not treating it as a Boolean anymore. It's treating it as a four value code, where these two are the sort of true cases. So we're saying it's not true this way and it's not true that way, and its level is greater than 0, which is what we said here. Then there's a possibility that we will return false. And when we return false, that's the same thing as saying go ahead and do this. So it's similar, but there's more logic now. What is the extra condition you have to pass? Well, we then say, well, let's take a look at L. And L goes through a logic that looks like, is it already known that we can't break L down? If it is, then say we can't break this down and spit it out. But if L could maybe be broken down, we push what we were doing onto a stack and resume iteration here. So yeah, we're now checking, is L redundant? So what doesn't happen here in the simple version is we don't go, hey, we looked at this variable here and saw that we haven't seen it yet. But we're wondering if maybe that variable, when we analyze it and break it down, it might turn out to be deduced from things that are inside of our learned clause. So this is digging in very deep. It would be like saying, the full deep version is like saying, okay, when we got here and we said that alpha was not learned, what if we broke down alpha and we found out that alpha was deduced from W and V? Then we would find out that actually alpha is dependent on what is learned, and therefore Z is dependent on Y, W, and V, right? And so Z could actually be removed then. So in the current version, we end up with alpha Y, Z, W, V. The deep analysis for redundancy has the quirk that it looks deeper into these variables. So it looks at variables like that alpha from the previous example. And so I assume that what actually happens here is when we look at alpha, we would put it on the stack, and we assume that when we then scan alpha, we find a bunch of simple cases. We go, oh, here's W. W is, it is seen, so it fails here. And then we look at V, and oh, V is seen, so it fails here. And so when it's done, it gets this path, which says, oh, okay, so alpha made it this far. So mark it as removable now. Even though it wasn't seen, so removable isn't a subset of seen. Removable are those things which, although they're not seen, can be treated that way because they are themselves dependent on, it's like their roots of dependency run down to things which are removable or seen. They're in the learned set, right? So we mark it as removable. And then we, pop that stack and go and look at P again now, saying like, oh, hey, we looked through it, and that thing you found that was not in your learned clause, well, even though it wasn't in your learned clause, we don't have to treat you as non-redundant. You might still be redundant. Let's keep going and looking more deeply to see if this is removable. All right, I think that's a pretty good picture of the analyze function now. Hello, welcome, Rhizoma. I think that might be how to say that name. How's it going? Okay, I feel pretty good about how I understand this now. Take a seat. Take a moment to lean back and think about next steps, I think. Rayzoma, do you know what a SAT solver is? So, okay, a SAT solver. Let me tell you what the problem. So SAT is the name of a problem, and the SAT solver is just a program written to solve the problem, or software. It doesn't have to be a program. I'm shooting for a library here, actually, but the SAT problem is a problem where it's a constraint kind of problem. So you give the SAT problem is set up like this. You are going to write down a big Boolean formula. Like you have Boolean variables, and you're going to combine them together using logical connectives like ands and ors, logical negation. You could add more stuff, but it stays Boolean. It doesn't go to being like a linear algebra problem. It doesn't deal with real numbers. It sticks with Boolean variables. And the goal is you are setting, if you're the one using a SAT solver and I was the SAT solver, then what would happen is you would write a formula and you would give it to me. So you're the user, you've created a formula, you've given it to me, the solver. As the solver, my job is to find a way to make all the variables, to give all the variables values that makes your formula true, or to let you know that there's no way to do that if it's impossible. And if it's possible to do that, we call it the formula satisfiable, and we give you the satisfying assignment. We say, here's a way to assign your variables values of true and false that satisfies your constraints. If the thing you give to me cannot be satisfied, there's no way to set it up, then I just say so. I let you know that I found that out. And that makes me the SAT solver. And that's it. That's the problem. That's what SAT is. So it's a thing where you input a Boolean formula and you ask, can this be satisfied? And it's called SAT, as in short for satisfiable. It asks, is this formula satisfiable? And usually the only easy way to find out if something is satisfiable produces as a side effect the assignment that satisfies it. So a simple example would be like, say you're playing a game of Sudoku, and so you have some rules about the game. Each square needs a number, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So there's 9 Boolean variables inside of each square, right? So you can be like, okay, if 4 goes in this square, then this variable will be true. But now there needs to be a rule that only one of those can be true. So we have a Boolean formula that's like, okay, 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. And we have another formula that's like, it cannot be 1 and 2. It cannot be 1 and 3. It cannot be 1 and 4, and so on for all the pairs. So it's a lot of little formulas, and we stick them all together. That makes one bigger formula that tells us how that square behaves, right? It can have 9 possible values. We use 9 Booleans instead of like 4. You could compress. You could represent the numbers 1 through 9 using fewer bits if you wanted, but it's a little easier to think of the logical formula that you would write if you use 9 bits for the numbers 1 through 9 there, right? And so that's a very easy example because that is a satisfiable thing. Like if I give you the number 5 as the solution, the number 5 represents a way to assign all those variables that satisfies the constraints, that one of them has to be true, but no pair of them can be true. That's the constraints. Now, if I make a grid of that, right, if I have not just one of those squares, but I take a copy of those variables and a copy of those formulas 81 times, then I've got a whole grid of them. And then I could start adding in more constraints. Like, okay, let's look at this row. Somewhere in this row there has to be a 1. Can I encode that? Well, sure. I take the 1 variable from each of the boxes in that row and say one of those or those together. This is a 1, or this is a 1, or this is a 1, and so on and so on and so on. And then I do the same thing with the pairs again. I say, it cannot be the case that this and this is a 1. It cannot be the case that this and this is a 1. And I do that for each pair of boxes. And in that way, I can build up the rule about how there has to be one and only one in the first row. And I can apply that to all the rows. I can apply that to all the numbers in all of the rows. I can also do that to all the numbers in all of the columns. And I can do something similar for all the boxes, the 3x3 boxes. And so I've built up, out of Boolean formulas here, a way to describe all of the constraints of Sudoku logically using Boolean formulas. And then what you could do is take that big block of Boolean formula, which it's got a few hundred conditions, it's got a few thousand conditions in it. And I think it's got, it's got 9 times 9 times 9. So it's got like 700-ish variables and a few thousand constraints, I think. And if you can take that and feed it into your solver and it can produce a solution,
then it can generate solutions for it can produce a solution to your Sudoku. And if you then wanted to, you could go in and like set some of the numbers. You could be like, oh, I have a Sudoku board here, and let me plug those in. So you fix some of the variables, you fix their states ahead of time, and then ask it to fill in the blanks from there. And so now you have a Sudoku solver. Might not be the most efficient way to build a Sudoku solver, by the way, because there's a lot of structure that you're throwing away by turning it into this just Boolean formula problem when it could really be some sort of like integer set logic system. But it's a very nice, easy to use base layer to get you started with constraint stuff, and then special constraints for systems for special problems can accelerate things like a Sudoku board. But if you had like a fun Sudoku board with more than just basic Sudoku rules, and it's got like, less than and greater than signs that relate certain parts of the board, and it's got, some Sudoku boards have rules like you cannot have, in addition to all the normal rules, you can't have knights move. So I can't have a 3 and knights move away from another 3, or a 5 and knights move away from another 5, right? If I add one of these new rules, a traditional Sudoku solver might be quite a bit harder to retool to have one of these rules in it. Whereas for a SAT solver, it's just a matter of coming up with the new Boolean formulas for expressing those constraints and throwing them in. So it's a nice interface for easily programming certain kinds of constraint solving problems, even though it does suffer from being so generic that it sometimes isn't. It rarely is a very efficient solution to a problem. In the sense of like, if you're going to be repeating this, if you have a class of problems that you need to solve lots and lots of big instances of that class, SAT might not be right. But if you want a tool that lets you specify a solver for a problem that you've run into in the wild on the fly, it's pretty flexible. Yeah, it's kind of like assertion. So an assertion is different in the sense that, like, if you talk about assert as in like in C code, assert basically says this has to be true or stop here. And this is like saying, what if the variables in your expression weren't fixed and you wanted, it's kind of like, you ever, here's a good example of this, right? So a basic example of a constraint problem is if you're ever like in, your basic algebra class. I think this shows up in algebra 1, maybe in algebra 2. I can't quite remember. But you get something like, okay, we're going to have like 2x plus 5y equals 10. And, then x plus 3y equals 0, right? And then you have to ask, well, what are the values for x and y? In this system, constraints are given to you, but x and y are like unknown variables. They're variables, and they're variables not in the sense that they contain a value, but they're variables in the sense that they stand for an unknown. And the same thing is going on here. When you write your SAT problem, what you're doing is you're saying, I don't know what values these variables have, and you're asking the SAT solver to find out what values they could have. And the Boolean formula is like these equations. It's the constraints that says, okay, they are variables, but they can't freely be anything. I need you to make them have values that hold to these particular constraints. So you're asserting the constraints in the sense that the solver has to satisfy those constraints as it finds values for the variables, for the unknowns. Now, where I'm at is I've actually kind of finished reading through MiniSat. MiniSat is a solver that I wanted to look at, and I think I've seen enough of it to understand its big ideas. So we've been at it for 4 hours. I think this would be a good time to stop. I was hoping to, I think someday, maybe next time I bring up the SAT stuff, we'll spend a bit more time
on the other half of this. So I've done two of these code reading things. Let's go take a quick look at where this is headed next. So I've got my FatSat stuff. And FatSat is already a working CNF solver using the CDCL algorithm, although it doesn't use any of the optimizations that we just saw in MiniSat. It's also it could undergo a number of improvements just by doing passes over it. I've learned a little bit how to organize literals and variables better from MiniSat, which had some good, better low-level ideas than what I've got here. I know that I want a smarter picture of clauses and need to think through how I'm going to do stuff that MiniSat was doing, like using the order of literals as a sort of shuffling the order of literals around as a state of the solver internal state kind of trick. Those seem like useful things to take advantage of that I learned from the MiniSat reading. And there's some other stuff. So let me make a to-do list of what I want to do in the FatSat project. And I think that's where we'll stop today. So that's kind of, my head is at what to do next. So there's optimization pass over FatSat. Right, so that's one thing we could do is we could go over the FatSat code I've got and put in some, why don't we, instead of saying optimization, we'll do cleanups. We'll just make some changes and adjustments, planning for, taking advantage of small changes like how to organize literals and variables that I've learned, and setting up for the coming features that I've learned how to build, or optimizations that I might want to do. So that's the cleanup pass. I think at some point we need to build a priority queue, a heap type structure. I think at some point I want to build the CNF from formula stuff. So this is a totally different chunk of problems we haven't looked at yet, but I've actually done a little bit of reading to get ready for it. So there's like a naive version, and then there's the I think it's this, was it? Like this. Yeah, then there's this part, which is cool, and we definitely want, oops, stop it. We want this. And then I think we want solver visualization. Solver process visualizations. Then I want to do a series of optimizations over the main solver. And I want to pull out to a standalone library. We might want at that point a Dymax parser option. Yeah, I think that's a good to-do list. This belongs down here with the optimizations. Some other optimizations we want are we want to use the watchers structure the MiniSat uses, and we want to use it's not the watchers. What's the other thing they were? Oh yeah, we want to use the like faster analysis algorithm that we learned from MiniSat. Okay. All right, that's my long-term to-do list. I think the next steps of this project will not be code reading. We will get to start hacking on this. So if you've been watching and you're here with me now, thanks for hanging out today. A couple notes. If you are following the streams, I'm doing Mondays and Fridays with a sort of plus or minus one day sometimes. On Mondays, I work on my big project and I try to do like something I need to make progress on. On Fridays, I kind of just do whatever makes me feel like I'm gonna have fun. And sometimes it's this MiniSat side or this sat solving side project. But I've been toying with some other ideas. I'm thinking next week might be different. Next couple weeks might be different. I'm not quite sure when certain projects are going to get started, but I'm thinking about looking at things like I might try to build some open source games that I really like and learn from their code a little bit, so do a little code reading on another genre. I'm also thinking about toying around with a compiler backend, TB by Yasser. If if you're curious which one I have in mind, and I'm just waiting on a good time to start that. So there's some other big fun ideas I have about stuff to do on Fridays. On Mondays, I'm working on the story engine stuff. And in general, if you want to be catching projects, you can come to mrforth.com and you can see projects I've already worked on. And under news, you can catch updates on other big things I have going on from time to time. And besides that, yeah, have a great day. Bye.